esperen. Espérate, espérate.
Yo creo que yo. Voy a entrar al celular también, porque no sé, tengo miedo. ¿Dónde está mi don?
¿Ya, Dubi? Sí, ya son las 2:21.
Llega, puedes volver a hablar, porfis. Ya. Ya pillé una cosa. Háblalo.
Muy buenos días. Vamos a dar inicio a la apertura del evento. ¿Alguien que me confirme si me escuchan bien, por favor?
Sí.
Sí.
Ok. Buen día, damas y caballeros. Es un placer para nosotros, en representación del equipo organizador del ICMAM 2022 y de su comité científico, dar apertura a la Conferencia Internacional Multidisciplinary Aspects in Mathematics and its Applications, ICMAM 2022. Los acompañamos en esta ceremonia la matemática Jessica González Hurtado, organizadora del evento, el presidente del comité científico, Duván Cardona, y yo, Brian Grajales, como presidente de este evento.
On behalf of the organizing team and scientific committee, we welcome all of you to the International Conference of Multidisciplinary Aspects in Mathematics and its Applications, ICMAM 2022. The president of this event, Brian Grajales, the president of the scientific committee, Duván Cardona, and me, as Jessica González, are going to conduct you the opening of this conference.
Como es sabido, nuestros tiempos evolucionan con un ritmo mucho más acelerado de lo que lo hacían hace algunos siglos. La ciencia nos ofreció la posibilidad de cambios sin precedentes en los siglos XIX y XX, y en esas transformaciones, las ciencias exactas y en particular la matemática han sido fundamentales, tanto para el desarrollo industrial, económico y financiero, político y de planificación o proyección social, médico, biomédico, espacial. Nuestro oficio ha contribuido a consolidar en buena medida el bienestar que han alcanzado las sociedades actuales y también nos ayuda a divisar el panorama para afrontar los problemas de nuestro tiempo y solucionar los errores que también hemos cometido en el pasado.
As we all know, our times are evolving at much faster pace than they did a few centuries ago. Science offered us the possibility to unprecedented changes in the 19th and 20th century, and in the exact science, in particular mathematics. Our profession has contributed to industrial, economic, and financial development, political planning or social projection, medical, biological, and space exploration. Our profession has contributed to the achievement of today's society. Mathematics helps to face the problems to our times and solve the mistakes of the past.
El siglo XXI entró con muchísima fuerza, estrechó nuestras comunicaciones y las hizo más rápidas. Fueron resueltos problemas del milenio que nos han retado desde hace mucho tiempo y sobre todo, en la base de los cambios, por un lado, experimentamos una sofisticación tecnológica en todas las esferas de la vida que, si bien son herederas de los esfuerzos pasados, no tienen precedentes como las misiones espaciales en Marte, los avances en seguridad informática y la importancia de esta para el bienestar de las naciones, los avances matemáticos en materia de medicina y en general la profundización del conocimiento del universo y de nosotros mismos. Pero tenemos que recordar que por otro lado, en la base de estos cambios, en el fundamento de esta arquitectura del avance, se encuentra la matemática como uno de los pilares más sólidos y generosos del haber científico.
The 21st century came with force. Communication and connectivity have improved faster. This century we have solved problems that have challenged us for a long time. We expected a technological sophistication in all the spheres of life that are thought inherited from past effort and improvements, such as the space mission to Mars, the advances in computer security, and the importance of this for the well-being of nations. In general, we have gained a deeper knowledge of the universe and ourselves. But we have to remember that the foundation of this architecture of progress is mathematics, as one of the most solid and generous pillars of the scientific legacy.
Es tan fuerte el potencial de la matemática que puede incluso fabricar la destrucción, como nos lo enseñó el siglo XX y como nos lo sigue enseñando el desarrollo de los conflictos actuales, principalmente en materia de perfeccionamiento armamentístico y en el hallazgo de nuevos flancos de guerra, como la ya mencionada seguridad informática de las naciones. Por eso es importante que los matemáticos del mundo, y en este caso desde y para Latinoamérica, nos pongamos más lugares de encuentro, a fin de que diseñemos redes de interacción científica para extraer todo el bienestar que nos sea posible de esta hermosa ciencia. Porque no podemos olvidar tampoco que, si bien la matemática estudia el universo y su lenguaje, lo hace de una forma activa, de forma que la matemática también produce el mundo, y se muestra entonces como necesario deliberar desde la matemática en clave del bienestar de la especie. Son palabras grandes, sí. Son problemas grandes, sí. También, pero a eso nos dedicamos, a solucionar problemas.
The power of mathematics is so strong that it can be even manufactured destruction. As the 20th century taught us, the current conflicts continue to develop the field of weapons, and also we have discovered new conflicts that involve the cybersecurity of nations. To benefit only from the positive impact of mathematics, it's important that the mathematicians of the world, and in this case from Latin America, created more meeting spaces to design networks of scientific interaction and cooperation to obtain all the positive benefits that we can from this beautiful science. Because we cannot forget that although mathematics studied the university and its language, it does so in an active way. So mathematics also produce the world, and it is therefore necessary to use mathematics to improve the well-being of humanity. These are big words. These are big problems, yes, but that is what we do, we solve problems.
En 1972, la tripulación del Apolo 17, con el Sol a sus espaldas, tomaba con fotografías la primera vista completa del planeta. Ello nos trajo una conciencia de conjunto, de que todas las naciones habitábamos un mismo lugar, lo cual se tradujo en acuerdos y preocupaciones científicas, principalmente con fines medioambientales. Tal vez esa idea de conjunto tendió a perderse en el tiempo, hasta que a finales de 2019 y a lo largo de 2020, las ciudades de todo el mundo se vaciaron y la pandemia nos recluyó, aislándonos, pero también recordándonos esa conciencia de conjunto. Fue algo que nos golpeó a todos, fruto de ese encierro y del lugar de la comunicación virtual que se tornó protagónico entonces, y en un contexto de boom de los eventos virtuales, nació la primera versión de este, ya hace 2 años.
In 1972, the Apollo 17 crew took the first photographs of the complex value of the planet. This brought the awareness that all nations inhabit in the same place, which translated into agreements and scientific concerns, mainly for environmental purposes. Perhaps the idea of togetherness got lost in time until the end of 2019 and through 2020, cities around the world were secluded due to the COVID-19 pandemic, which remind us of that awareness of togetherness. It was something that hit us. As a result of that confinement, virtual communication became the protagonist with a boom of virtual events that when this conference was born 2 years ago.
Inicialmente se trató de un encuentro dado por la amistad, entre algunos que coincidimos en el deseo de entablar un diálogo bajo las condiciones comentadas. Iniciamos entonces Milton Aguirre, Karina González, Jessica González, Brian Grajales, Sergio Troncoso y Duván Cardona, quienes nos conocíamos desde hace ya 14 años en Cali, Colombia, particularmente en la Universidad del Valle. Ahora se podrían mencionar 3 objetivos que nos guiaron entonces. En primer lugar, una de nuestras motivaciones más importantes era honrar a nuestros maestros. Por eso se ofrecieron entonces galardones a dos matemáticos de la Universidad del Valle, Gonzalo García y Roberto Ruiz, y tres homenajes póstumos, Guillermo Restrepo, Ana María Sanabria y Doris Sinestrosa. En segundo lugar, queríamos encontrarnos con otras personas del país, del continente y del mundo, que estuvieran haciendo matemáticas para así fortalecer los lazos. Y finalmente, queríamos presentar nuestros trabajos enmarcados en una tradición científica para los estudiantes que comienzan este camino.
Initially, this was a meeting of friends, with the desire to engage in a dialogue and scientific discussion. We started with Milton Aguirre, Karina González, Jessica González, Brian Grajales, Sergio Troncoso, and Duban Cardona, who had known each other for 14 years in Cali, Colombia, particularly at the Valle University. The three objects that guide us back then were, first, honor our teachers. Therefore, awards were offered to two mathematicians from Valle University, Gonzalo Garcia and Roberto Ruiz, and three posthumous tributes to Guillermo Restrepo, Ana María Sanabria, and Doris Sinestrosa. Secondly, we wanted to meet other people from all the world who are doing mathematics to strengthen the scientific community. And finally, we wanted to present our work framed in a scientific tradition for students who are beginning this path.
Así, en 2020, el evento logró contar con la participación de 12 países. Y en su segunda versión, que presentamos hoy ante ustedes, contamos con la participación de más de 40 países, tratándose ahora de un evento organizado con el apoyo de la Sociedad Colombiana de Matemáticas, la Facultad de Ciencias Naturales y Exactas de la Universidad del Valle y el Departamento de Matemáticas de la Universidad de Pamplona. De esta manera, y continuando el inicial propósito de rendir homenaje a nuestros maestros, en esta ocasión queremos rendir un muy sentido homenaje al profesor José Raúl Quintero por su participación en la construcción del Departamento de Matemáticas en la Universidad del Valle y sus contribuciones en lo que llamamos construir escuelas. Por personas como él, se ven impulsadas las matemáticas en Colombia y especialmente desde la universidad pública, que como ustedes saben, atraviesa problemas históricos de financiación. La función es indispensable para el desarrollo del país y para pensar y atraer un mejor futuro.
So, in 2020, the event managed to have the participation of 12 countries. Today, the second version in this conference has the participation of more than 40 countries, and it is being organized by the Colombian Society of Mathematics, Department of Exact and Natural Science of Valle University, and Department of Math of Pamplona University. In this way, we continue the initial purpose of honoring our teachers. On this occasion, we want to honor Professor Raúl Quintero for his participation in the creation of the Department of Mathematics at the Valle University, and his contributions, what we call building a school. Thanks to people like him, mathematics in Colombia has improved, especially in the public university, which, as some of you know, most of you know, it's going through a historical problems of funding and infrastructure. But that function is indispensable for the development of the country and a better future.
El profesor Raúl Quintero lidera el grupo de investigación en ecuaciones diferenciales parciales y geometría en la Universidad del Valle, donde funge como decano de la Facultad de Ciencias Exactas y Naturales desde mayo de 2021. Ha sido director del posgrado en Ciencias Matemáticas y vicedecano de Investigaciones y Posgrados de la misma facultad desde el año 2015. El profesor Quintero es egresado de esta misma universidad y realizó estudios de doctorado en matemáticas en la Universidad de Maryland, Estados Unidos. Finalmente, este fue galardonado con el Premio de la Sociedad Colombiana de Matemáticas y ha sido incorporado como miembro de la Academia Colombiana de Ciencias Exactas, Físicas y Naturales. Por su excepcional aporte y ejemplar trayectoria, Le rendimos homenaje, estimado y apreciado profesor Raúl Quintero.
Professor Raúl Quintero leads the research group in partial differential equations and geometry in Valle University, Cali, Colombia, where he served as Dean of the Faculty of Exact and Natural Science since May 2021. He has been director of the graduated program in mathematical science and vice dean of research and graduated studies of the same faculty since 2015. Professor Quintero is a graduate of this same university and completed his doctoral studies in the same university, in mathematics at the University of Maryland, United States. Finally, Professor Quintero was awarded the prize of the Colombian Society of Mathematics and has been incorporated as a member of the Colombian Academy of Exact, Physical, and Natural Science. For your exceptional contribution and exemplary career, we honor you and admire you, Professor Quintero.
Es nuestra ambición posicionar este encuentro dentro de la tradición de eventos académicos de matemáticas que tienen lugar en América Latina, como el Congreso Latinoamericano de Matemáticas. Por eso, los hacemos partícipes a todos ustedes de la gran alegría de presentar el ICMAM 2022, que se ofrece como el primer evento de esta naturaleza en Colombia, sustentando su fortaleza en la calidad de los panelistas y speakers, entre quienes contamos con Carlos Koenig, presidente de la Unión Internacional de Matemáticas, y con dos de las mentes más brillantes de nuestro tiempo que han sido galardonados con la medalla Fields, que como ustedes saben, es el homólogo del Premio Nobel en nuestro campo. Se trata de Simon Donaldson y Terence Tao. A continuación, procederemos a presentar el equipo de académicos que ustedes escucharán en esta ocasión.
We want to position this conference within the tradition of academic events of mathematics that take place in Latin America, such as the Latin American Congress of Mathematics. Therefore, we, with great joy, we present you ICMAM 2022, which is the first event of this nature in Colombia, with high-quality panelists and speakers, such as Carlos Koenig, President of the International Mathematical Union, and two of the most brilliant minds of our time who have been awarded the Fields Medal, which, as you know, is the counterpart of the Nobel Prize in our field. They are Simon Donaldson and Terence Tao. I will now proceed to introduce the team of scholars that we are going to participate in this occasion.
Entre los panelistas y speakers de este evento, contamos con la presencia de
Among the panelists and speakers of this event, we have the presence of
Terence Tao, UCL, USA, Michael Ruchansky, Ghent University, Belgium, Enrique Suazua, Friedrich University, Germany, David dos Santos Ferreira, Institut Elie Cartan, Université de Lorraine, France, Carlos Koenig, President, International Mathematical Union, Simon Donaldson, Imperial College, London, UK, Harald Helgoff, Alexander von Humboldt, Professor, University of Göttingen, Germany, Diana Toro, Director, Simons Laufer Mathematical Science Institute, USA, Christine Lauter, Facebook, Toru Osawa, Waseda University, Japón, Manuel Del Pino, University of Bath, UK, Andrés Villaveses, Universidad Nacional de Colombia, Boris Silver, Oxford, UK, Thais Jordao, University of Sao Paulo, Brasil, Paula Cerejeiras, University of Aveiro, Portugal, José Raúl Quintero, Universidad del Valle, Colombia, Felipe Rincón, University of Bath, UK, Andreas Bayerman, Ghent University, Pavle Dragojevic, Freie University, Berlin.
Con el aporte de todos ellos, esperamos componer un panorama balanceado del desarrollo contemporáneo de las matemáticas, que va desde los temas más abstractos como la lógica, la teoría de números, el análisis de Fourier o las ecuaciones diferenciales, hasta los más aplicados como la teoría de control, inteligencia artificial, big data o criptografía. Especial mención queremos a Tatiana Toro, quien es egresada de la Universidad Nacional de Colombia y ejerce como profesora de la Universidad de Washington. Su investigación versa sobre ecuaciones en derivadas parciales, análisis armónico y geometría de la medida. Recientemente fue nombrada como directora del Mathematical Sciences Research Institute para el periodo 2022-2027 y como es de conocimiento público, se llevará a cabo su nombramiento como vicepresidenta de la Unión Matemática Internacional, con lo que se trata de la primera colombiana que nos representa en esta instancia internacional. Por su riguroso trabajo y ejemplar trayectoria, muchas gracias, profesora Toro. Es usted un faro en nuestra labor.
With the contribution of all of them, we hope to represent a fair panorama of the contemporary development of mathematics, rising from the most abstract topics such as logic, number theory, Fourier analysis, or differential equations, to the most applied ones such as control theory, artificial intelligence, big data, and cryptography. We would like to make special mention of the Colombian mathematician Tatiana Toro, who graduated from the National University of Colombia and is a professor at the University of Washington. Her research deals with partial differential equations, harmonic analysis, and geometry of measurement. She was recently appointed as director of the Mathematical Science Research Institute, MRSI, for the period of 2022-2027. And as is a public knowledge, she will be the first Colombian vice president of the International Mathematical Union. For your rigorous work and exemplary trajectory, thank you very much, Professor Toro.
Por otro lado, quiero compartir con ustedes una muy grata noticia. A partir de esta versión de ICMAM 2022, nos complacemos en presentar el premio ICMAM Prize, que será otorgado a uno o más matemáticos colombianos, quienes destacan por sus fundamentales contribuciones en matemáticas puras o aplicadas, así como por sus contribuciones a la visibilidad internacional de la comunidad de investigación matemática colombiana. Los candidatos a este premio podrán ser nominados especialmente por miembros del comité organizador del ICMAM y a su vez podrán postularse por sí mismos. Felizmente, les anunciamos que durante el desarrollo de este evento tendrá lugar la primera versión de este premio.
On the other hand, I want to share with you very pleasant news. Starting with this version of ICMAM 2022, we are pleased to present the ICMAM Prize, which will be awarded to one of the more Colombian mathematicians who stand out for their fundamental contributions in pure or applied mathematics, as well as for their contributions to the international reputation of the Colombian mathematical community and research. Candidates for this award are nominated by members of ICMAM organizing committee, and also they can nominate themselves. We are happy to announce that during the development of this event, the first version of the award will take place.
Finalmente, queremos terminar estas palabras de apertura presentando de forma sintética al Comité Científico del ICMAM, quienes han contraído la responsabilidad de proponer y gestionar la comunicación e invitación de las personalidades que ustedes escucharán. El comité estuvo conformado por 8 matemáticos así.
Finally, I would like to end these opening remarks by synthetically introducing the ICMA Scientific Committee, who had assumed the responsibility of proposing and managing the communication and invitation for all mathematicians. The committee has formed by 8 mathematicians.
Uwe Kaller from Portugal, President of the International Analysis Society. Alicia Dickstein from Argentina, former Vice President of the International Mathematical Union. Mitsuru Sugimoto from Japan, member of the Japanese Mathematical Society. Emmanuel Carneiro from Brazil, the Abdus Salam International Center of Theoretical Physics. Alphonsus from Colombia, President of the Colombian Society of Mathematics. Claudia Gareto from Italy, Queen Mary University of London. Thais Jordan from Brazil, University of Sao Paulo, and the President of the Scientific Committee, Duan Cardona from Colombia, Ghent Analysis and PD Center.
Es nuestro deseo presentar este evento de forma bianual, continuar homenajeando a nuestros maestros y consolidar un escenario en Colombia y Latinoamérica de pensamiento matemático de alto impacto para la ciencia latinoamericana. Por favor, disfruten las presentaciones. Muchas gracias.
We desire to present this event on a biannual way to continue honoring you, professors, and to consolidate a scenario in Colombia and in Latin America of thinking with high impact on Latin American science. Please enjoy the conference. Thank you very much.
Ok, muy bien. Nuestro primer conferencista es el profesor Andrés Villaveses. Our first speaker is Professor Andrés Villaveses from National University of Colombia. So, Professor Villaveses, thank you very much for accepting our invitation. Milton Aguirre will share you in this for your conference, okay?
Great. Okay. Thank you very much.
Buenos días. Buenos días para todos y todas. Soy Milton Manuel Aguirre, miembro organizador del ICMAM 2022. Y es un placer para mí presentar quien abrirá con llave de oro nuestro evento. Él es el profesor Andrés Villaveses. El profesor Villaveses es un reconocido lógico colombiano que ha hecho importantes contribuciones a la lógica, la teoría de conjuntos y a la teoría de modelos. Él es el actual director del Grupo de Lógica de la Universidad Nacional de Colombia.
Good morning, everyone. Milton Manuel Aguirre, organizing member of ICMAM 2022, has the pleasure to present who will be open or even with a golden key. He is the Professor Andrés Villaveses. Villaveses is a recognized Colombian logician who has made important contributions to logic, set theory, and model theory. He is currently the director of the logic group at the Colombian National University.
Comenzó su camino matemático trabajando con Xavier Caicedo en Bogotá, Colombia, en la teoría de modelos sobre poleas. Luego, durante su doctorado, trabajando con Ken Kuhnen en Madison, Estados Unidos, en la teoría de conjuntos. Su próxima parada fue en Jerusalén, donde realizó estudios de postdoctorado con Saharon Slav, y fue aquí donde comenzó el largo camino hacia la teoría de modelos de clases elementales abstractas. Esta es una enorme tarea que tiene una mezcla fascinante entre la teoría de modelos y la teoría de conjuntos, como él mismo lo describe.
He began his mathematical work with Xavier Caicedo in Bogotá, Colombia, on the model theory of shapes. During his PhD, working with Ken Kuhn in Madison, USA on set theory. His next place was Jerusalem, where he did postdoctoral studies with Saharon Shelah. And it was here that he began the long road to the abstract theory of the elementary class model. This is a huge task that has a fascinating mix between model theory and set theory, as he himself described it.
Sus intereses de investigación actualmente se centran en la teoría de modelos, teoría de la estabilidad de clases elementales abstractas, conectadas con geometría, teoría de modelos de poleas, con teoría de modelos de invariantes modulares, y teoría de modelos conectada con la teoría de conjuntos y la lógica infinita.
His research interests currently focus on model theory, stability theory in abstract elementary classes, related to geometry, model theory of shapes, model theory of modular invariants, and model theory related to set theory and infinite logic.
Una característica marcante del profesor Villaveses es su fuerte interés por la filosofía de las matemáticas.
An outstanding characteristic of Professor Villaveses is his great interest in philosophy of mathematics.
Es lindo recordar cuando la Academia Colombiana de Ciencias Exactas, Físicas y Naturales lo reconoció como el mejor investigador joven en el año 2000.
It is so nice to remember when the Colombian Academy of Exact, Physical and Natural Science recognized him as the best young researcher in 2000.
Su apreciación sobre los enlaces tenues o incluso muy fuertes entre la lógica y otras ramas de las matemáticas hacen de él uno de los científicos colombianos más consolidados de nuestro tiempo.
His appreciation of the tenuous or even very strong links between logic and the branches of mathematics make him one of the most established Colombian scientists of our times.
Hoy, él nos compartirá una visión amplia de los posibles papeles de la teoría de modelos en el siglo XXI.
Today, he will share with us a broad vision of the possible roles of the model theory in the 21st century.
Bienvenido, profesor Villaveses, y adelante.
Welcome, Professor Villaveses, and go ahead.
Mil gracias. ¿Se escucha? ¿Me confirman si se escucha bien?
Sí.
Ok, sí, perfecto.
Yes.
Okay. Now my screen, is it visible at this point? You have the wide view of possible roles for model theory in the 21st century. Is the screen visible? ¿Se ve bien la pantalla, Duan?
Se ve bien, profesor.
Excelente, listo. Ok. Voy a decir un par de cosas en español, then I switch to English. Mil gracias. Primero que todo a Duan Cardona por haber, digamos, hecho el enlace de la invitación, y extiendo obviamente las gracias a todo el equipo grande e impresionante que ha organizado este evento, que como bien dijeron y tal vez no señalaron suficientemente, es absolutamente es el primer evento de este estilo que tenemos aquí. Quiero señalar adicionalmente que el equipo, a quienes conozco y sobre todo a Duan Cardona, es un equipo de profesores o egresados muy jóvenes de la Universidad del Valle que están liderando algo que realmente es muy novedoso para nuestra comunidad matemática en Colombia. So this is really wonderful. I feel very, very honored to be here, first of all, among this amazing crowd of mathematicians. So I feel honored, humbled also. And at the same time, I feel it's a great responsibility to open, with my lecture, this event. It's as I just said, it's quite a responsibility. I want to offer a kind of wide view, if possible, of possible roles for model theory in the 21st century. Of course, after I sent the title, I thought, well, 21st century is maybe too wide to know. I mean, so maybe I should have said in the next decade or in the next year or something like that. But that's how it is. Let us just take a quick look at the photograph. It's a photograph I took in Cali. This is Cali. These are the mountains of Cali, and this is the Farallones. This really kind of offers us kind of a replacement for not being in Cali. Of course, we all wish we would, could be, present in that wonderful city. But I really want to open up with this very wide view. Now, I apologize both to logicians and to non-logicians, to mathematicians who are not logicians for repetitions of things that you know very well. And non-logicians, hopefully, I'll try not to annoy you with all of these definitions of logic, but I will try to connect some aspects of logic with the parts of mathematics that are outside. So our path will have essentially 3 steps and then a summary of perspectives. The first step is wide model theory. So I'll try to describe a little bit of, a kind of very perhaps personal, although it is shared with many of my colleagues, view of what model theory may be used for. Then in the second part, and beyond first order logic. So the first part will happen in first order logic, and the second part will try to open up what is happening in the past, essentially 2 to 3 decades in model theory. Then a little bit more details of perspectives of what is happening beyond first order, some of the things that are beginning to happen. Some of them may evolve into many different directions. You will see one of those directions tomorrow here. Boris Zilber is one of the main proponents of one of the directions that I will speak about in the last part. But let us now start with our why model theory. But I wanted to give you the path where we go. So this is a kind of picture of the path. Definability is kind of one of the main features that we will start with, and then we'll see it becomes kind of tricky when you get outside first order, as we will see in a moment. So let us think about some mathematical taxonomies. Let us consider this question. Some mathematical structures we know very well seem less random, more canonical than others. Why is that so? So let us consider the formless magma, kind of random noise, perhaps, of all possible mathematical structures. We all know that there are many, many mathematical structures, but is it random noise? Well, perhaps, of course, I mean, if we are here, perhaps it's because we know it is not random noise. We know that there are some structures that are extremely important, and we want to know what happens inside them, like natural numbers or the complex numbers with, analytical functions or many. So, of course, we know that groups and fields and algebraic varieties and Sobolev spaces and inner modes of set theory and function spaces. I mean, I just mentioned here some structures in mathematics that are important to people here. We know that they're not quite random noise. They're important. So why? Is the world of mathematical structures a homogeneous world, or is there some kind of classification there? So we take this sort of a wide view. Model theory. One of the achievements it provides us with very strong classification tools for all first order structures. For all first order structures, it really provides that sort of classification tools. I want to speak a little bit about that. So I here have a list of structures that we know are important. For instance, the first one is the primary structure that is used in arithmetic. Of course, in arithmetics, there are many other structures that we build in order to understand questions about the natural numbers, or in algebraic geometry about the complex numbers, and the real algebraic geometry, the real numbers, vector spaces, or elliptic curves in a kind of more sophisticated world, or maybe some combinatorial graphs, or maybe some Hilbert spaces or Banach spaces or whatever. So you know that words like dimension, rank, or degree, or density character, they seem to appear attached to those structures. And they happen from many different parts of mathematics, dimension, and so on. And those words seem to kind of control those structures and allow us to understand them, to capture them in some sense. So in model theory, we start looking at arbitrary structures, and we take the risk of looking at completely arbitrary structures that may perhaps in and of themselves not be so important and so interesting, but we look at all of them in order to get some kind of hierarchy of types of structures or their theories. And their theories is a tool we use to understand them. That part of model theory is stability theory. I will speak a little bit about that in a moment. There are parts of the hierarchy. In the best part, generalized Zariski topology, well, there are aspects, Zariski geometries that are generalized Zariski topologies, those are due to Hrushevsky and to Zilber, who will speak here tomorrow. Arbitrary structures whose place in the hierarchy ends up automatically giving them some strong similarity to algebraic curves. I put here elliptic curves that's kind of more specific. So you start from very arbitrary structures and they end up looking similar to algebraic varieties or to elliptic curves. And that is somehow strange. Why does that happen? Well, there are also unidimensional objects there, and those are exactly finite covers of algebraic curves. And those correspond to structures that have been built to capture non-commutative phenomena in physics. So from 1 to 4, we jump very quickly from extremely general aspects and questions to, of course, after decades of model theory, to possible connections with non-commutative phenomena in physics. And that's already something that should trigger our interest, I think. Well, more recently, model theory has also dealt with limit structures of various kinds, limiting processes of constructions like mathematical approximation and perturbation theory, and they end up also being model theoretical in nature. So we have here an arc going from complete random to very specific and modern tools. But let us just look at the taxonomy. So the blurb here is the world of all possible structures. And there are, first of all, some dividing lines, some important dividing lines. Some of them have names that are important. The red one is the most important, stable. So all structures are divided into either stable, and that means they are similar to algebraic structures such as algebraic varieties or vector spaces on the left-hand side, or order property. And then everything is one of these two sides, and that's very strong. If they have the order property, they have an infinite order, so they are like the rationals, or perhaps like set theory or like arithmetic. So you see, it already divides flavors of structures, and it divides in the case of the red line in a very sharp way. That was the first major dividing line, by Scheller mainly. There are many other dividing lines. Those are much more sophisticated to define, like O top, no top, and so on. They divide according to different ideas, that world of all possible structures. But what we have then is, it is very non-random, but the tools to understand the non-randomness really come from looking inside the structures and looking at comparing the structures. The first line of this list is that red line, stable and stable. The other lines, you can just ignore them for now. They're just, specific ways of making this division. But the important thing is, after a few decades of looking at more and more dividing lines, we end up with a better kind of map of all possible structures. In this map, there is an area that is quite important, stable structures. Algebraically closed fields, the basis for algebraic geometry, are very much in that corner, that lower left corner. Then you have the opposite corner, the Gödelian area, where Gödel-like phenomena happen, like in set theory, or like in arithmetic, of course, as it happened originally. And then in between, you have a lot of interesting situations that are perhaps more similar to algebraic geometry, or perhaps more similar to the Gödelian area, or perhaps somewhere in between. Well, after a few decades, the map has become this much more detailed and fine-tuned. So Gabriel Conant has this site, Forking and Dividing, where it's actually an interactive site, where each red dot here is an important mathematical theory. You can click on it and see why it is placed in such and such taxonomical region. And you can also highlight taxonomical regions, like in pink here, I have stable theories. That was exactly the same, kind of lower corner here. But you have, it's very fine-tuned, and it is getting more and more fine-tuned. And for each one of these, you have, examples, and many of these examples are theories that people do work in different areas of mathematics. Of course, there is a question of which kind of mathematics are really amenable to first order, and that will be the second part of our lecture. But after a few decades, starting from essentially the late 60s, early 70s, until now, then you have, something like 40 years that are somehow subsumed in this interactive graph that is getting updated, as more theorems and more definitions are obtained and more theorems are proved about theories. So model theory, to summarize in a very quick way, many decades of very detailed work, has finally provided us with this sort of taxonomy where you can place a lot of structures. There are structures connected to graphs. There are structures connected, of course, to real algebraic geometry, to algebraic geometry over the complex numbers, to strange versions of algebraic geometries, to set theory and variants of set theory. There are many theories. Everything in every theory you can write in first order has some place in this map, and this is quite something quite extreme if you think about it. So not only do we have the map and we have the dividing lines, where sometimes, like in the stable case, the two sides of the dividing line have a lot of meaning. Being stable means you have a lot of control, very good dimension theory. Being unstable means you have an order, and therefore you can get a lot of information from the fact of having an infinite order, and you can actually know a lot of connections between different theories. So this gives you a very wide perspective. Sometimes the dividing lines are less sharp than the one I just described, and they refer to more internal, perhaps more detailed, fine-tuned aspects of the theories. But this is state of the art of first order model theory that is absolutely stunning and fantastic, and that is still very much going on and producing extremely interesting areas. Let me just mention here O minimality. O minimality has recently been linked even to theoretical physics. So the O minimal area here is outside the stable, but it shares with the stable a lot of extremely strong structural features. And so knowing that something is O minimal gives you for free a lot of information and perhaps theorems, or knowing that something is in some area maybe gives you a sense of how difficult it will be to obtain some kind of theorem that you dream of. Anyway, so this is a very quick, very rough description of what is sometimes called the map of the universe. As we will see, it is not quite the whole universe. It is a map of a universe, a very important universe. Now, there is, let me just mention this big aim in model theory that has been triggered by stability. Given any countable theory, you have the spectrum function counting the models of the theory in some cardinality. And there is this sort of asymptotic theorem by Saharan-Shelah that tells us that the function counting, it may have some kind of noise in the beginning, but in the end, every theory is split between kind of exponential growth in the number of models or very controlled growth. And there is something called the main gap in between those two. So this is a kind of a meta theorem connected to this map that somehow tells you what is the asymptotic behavior of the cardinal function counting the number of models of each theory. And it divides for all first order theories the world in two. Either are super exponential or they're very well controlled. I don't go into the detail. The detail is given here by this formula, but it doesn't matter what it means at the moment. What it means is that it is not exponential and it is really well controlled. So there is something here happening about all theories that is an outcome of model theory that is quite surprising. Let me just mention a little bit of spin-off from stability theory. So I think it is worth mentioning, and forgive me if my list here is incomplete. I think Khrushchevsky's proof of the Mordell-Lang conjecture from around 1990 was a major step in the in drawing from the theory. It is not just some adaptation of model theory, but there is something quite deep going on connected to the formation of this map. He was able to somehow get to the heart of what was needed for the Mordell-Lang conjecture. Later on, the André-Oort conjecture was kind of this is a continuation of that first line. There is a model theoretic analysis by Scanlon. I forgot here to put the name, but people. There, and much more recently, there is a proof by Casal, Freitag, and Naglu, the conjecture by Pain-Levé in differential equations. The conjecture is from around 1895, and it is proved by using the model theory of differentially closed fields. That's an important theory, an important point in the map that has drawn a lot of interesting applications. And very recently, a conjecture by Pain-Levé was proved, and much more information was gathered from model theoretical tools. There is also more theoretical analysis of analytic functions, but this part here will kind of become more important in the second part of our lecture today. So the original dividing line, the red one in the map, from whose name the whole subject inherited the name of the subject, is stable, unstable, or stable order, and the name of the subject is stability or classification theory. So let me go back to definability. So initially, let me go now, after this introduction kind of going very quickly into a map, let me just say that originally model theory was allowing two basic things. First of all, capturing classes of models, axiomatizing, like the class of all groups or the class of all fields or something like that. And also inside the models, it enabled us to isolate definable sets within each model of the class. So yeah, here each model. Here there are many examples here: piano axioms, the group axioms, the field axioms, algebraically closed fields, and so on. And inside there are definable sets. And let me just say a little bit more. You have a formula, you have logic, you have a formula, and then you have solution sets for the formula. Here's a classical example for you. So you want to say what is defined by the formula, and this is something that everybody here is familiar with. You're given an equation here, put some kind of a cubic equation, but it could be any equation in any language that is fixed, and you want to find the set of all solutions. For instance, here I find the set of all x, y in C squared, such that the formula, so they satisfy this equation. That solution set is a definable set, with a difference in model theory is that we can use formulas that are not necessarily equations like this, but they may come equipped with a lot of universal existential quantifiers. They may have a very complex looking form, but this idea of isolating the solution set of something that is very classical in mathematics, it harks back to centuries, to Descartes if you want, or even earlier if you want, is one of the main things we do in model theory at the beginning. Once you have formulas, you can ask what are the solution sets of these formulas, and we call them definable sets. Now, we can also look at sets of definable of formulas and kind of define something by being the solution, a little bit like what you do when you do. I want to look at the intersection between the solution to two equations or three equations or a system of equations, or maybe an infinite system of equations, as we do here in logic. But here, instead of taking an infinite system of equations, you take an infinite set of formulas. And in many cases, there are interesting things happening here. It's so important that these are really what I would call the building blocks of model theory. Types, they're called. So a type really is some kind of you can look at it as an infinite set of formulas that you want to solve, and that you might be able to solve, or maybe be able to solve somewhere. Here's an example: the type of 2 over q. That's, it is trivial because it's all given by the formula x being 1 plus 1, and all the consequences of that. A slightly more interesting type is this type of the square root of 2 over q. Here, the equation is slightly more complicated. You have to say x times x is equal to 1 plus 1, or x squared is equal to. A more interesting type, or a type you cannot really reduce to one formula, is to say, no, I am not a solution to any polynomial over the rational numbers. So that would be the type of pi, but notice that this is also the type of e over q, and the type of any transcendent number over q will be shared. So this is a description of not being algebraic, but this description of not being algebraic is the description of a possible type. And we have a very kind of naive classification of types here. The first one is realized. The second one is principal. It is generated by one formula. And the third one is not generated by one formula, but it's still, as we know, it's extremely meaningful. It's perhaps the most interesting of the three types. This is just an example to give you a flavor of what we call a type. Now, as we do in mathematics all the time, we turn things around. We may regard a set of formulas as corresponding to a kind of definable, generalized definable set. So we can look for the solutions in some model, and that yields the type definable. So we have first the definable sets, and here you have the type definable sets by essentially taking, like the common solution to all the formulas that appear in the type. And you can do this, to find type definable subsets of m squared, of a model squared, or in the cube, depending on the number of variables that your formulas in the type have. This is kind of picture here. So P here would be the type, and here would be the solutions. And here, this base, the green base, would be the kind of basic set over which you describe the type. And you can have some different types here. And they start looking at some kind of geometric configuration. So this kind of drawing, kind of naive drawing of the type, is made on purpose, because a little bit like what happens with ideals in algebraic geometry, like Hilbert's Nullstellensatz, the crucial information on varieties is captured by radical ideals. Something like that happens sometimes in types. So in the complex numbers, A and B have the same type, or V is captured by ideals. In general, these will be the basic blocks of information, and they will allow us, well, do all the, all the process that led to the map that I described before is kind of based on first understanding how these types behave, interact with one another, what happens if you reduce or increase the number of variables or parameters in your types. And by turning things around, something happens that types in model theory can be seen in many different ways. I gave you a description as sets of formulas. There are also Zariski closed sets in some topologies. There are also orbits and there are morphisms, the monster models, really large models. There are also, in some more recent treatments of types, there are measures and states, or there are distributions. So when an object in mathematics looks, you have 4 or 5 or whatever equivalent definitions coming from different ideas, different sets of ideas, like orbits. Orbits suggest Galois theory, measures, states, distributions, sets of formulas. We know as mathematicians, we know we are in front of something that may not just be bypassed and cast aside. So types are really the versions of definable sets that we want to look at in model theory that are really useful. So let me just state some of the advantages of first order logic. First of all, it gave us the map. The classical relation between theories and classes of models of the theories has been extremely productive, and it has provided many things. I won't go into details here. These are parts of what is normally learned in a model theory class, like in our undergraduate model theory class. Let's say here at Universidad Nacional de Colombia, some students are here. You learn about ultraproducts, compactness, type spaces, their topologies, and the connection to unions of chains of models. All of this is kind of the description of basic model theory that is doable with all these first order tools. It is extremely rich, and it has a history that harks several decades, even before stability, and then it exploded with this stability theory that I was describing in a moment. So before switching to our to next, to the examples and to the change, let me just mention here that there have been several descriptions of model theory. In '72, for instance, Chang and Kisler's in their major fantastic textbook, they described model theory as universal algebra plus logic. So you want to do kind of constructions of models and classes of models you do in universal algebra, but use logic to control them, as we have been seeing. In '93, Hodges redefined model theory by the equation, it's algebraic geometry minus fields. It's kind of pun, a kind of joke. They say, well, we try to do what we do in algebraic geometry, except we don't want to be controlled by fields. We want to make it more free. In 2009, Khrushchevsky described it as the geography of tame mathematics. And that's a very interesting description that I cannot really go into more detail here. It takes longer to see what is going on here, but we will see a little bit of that in a moment. Okay, let me just go to a very classical application of first order model theory, the Steinitz theorem from more than a century ago showed that all uncountable algebraically closed fields of characteristic 0 of same cardinality must be isomorphic. That's called categoricity in T, and countable cardinality for algebraically closed fields of characteristic 0. Now, that theory is included in the complete theory of the complex numbers. Of course, the complete theory satisfies all the axioms. But the small theory, ACF0, is axiomatizable in a recursive way. You can write the axioms of it's the field axioms and solutions to all non-constant polynomials, characteristic 0. You can write those axioms. And then the categoricity, so the first blurb here implies that that theory, the small theory, is complete and therefore must be equal to the complete theory of the complex numbers. So to check whether a sentence, sigma, is true or not in the complex numbers, you just run using the recursion, in blurb 3, all consequences of the axiom. And the completeness will do the trick. Everything will be decided. So there is no role to prove theorems over the complex numbers unless we change something, you put exponentiation. But this is the classical, very classical, more theoretic argument of this. This decidability of the complex numbers was also, found in different ways. But this is a very kind of a quick exercise in basic model theory. So this is kind of an up and down phenomenon that is strengthened in extreme ways in stability theory. Classical is also X-Coaching. So this, I think, because we started a little bit late, let me just mention the result that we use model theory, and especially this last part that we are taking here, ultra products of finite fields given by power series, formal Laurent series, or finite fields, and we use the finiteness of these, and we use the product of the primes. So this, sorry if I don't go into detail here because I want to get to something else later, but this is already more sophisticated than the previous slide where you got the decidability of arithmetic, and this already was opening an important way of applications of model theory. In this case, well, it's really about Henselian value fields, and this story has continued in many different ways. But at some point, there is some lemma that where we want to guarantee that two structures that look different, in fact, satisfy exactly the same formulas. The structure here, the ultra product of the FP power series of T, and the ultra product of the QP. But I won't go into more detail of this here. The third major step that I want to mention in first order model theory, that I already mentioned it, but I want to say a little bit more, the solution to Mordell-Lang's conjecture over fields of arbitrary characteristic by Khrushchevsky in around 1990, used much more sophisticated ideas. So there was an evolution from very classical ideas for decidability of the complex numbers to less classical ideas for X-Coaching, to a really much deeper model theory here used, it has analysis of so-called modular sets and generalized Zariski context and the analysis of unidimensional. This dimension here is a model theoretic dimension. Geometric model theory, really at its deepest, is used here to solve a major question in the 20th century of number theory. So these are all major steps accomplished in first order model theory. There have been other developments along this line. I mentioned here just a few, but let us now take a turn and go to what else is happening and what happens beyond first order logic. So what we had before was this sort of crescendo from questions about definable sets to questions about types, and I told you those are the really important things, and types are orbits, and they support, as I shall mention a little bit later, a kind of Galois theory. And then the crescendo ends up in that map, the map that I showed, that gives you all classification. The map is connected to asymptotic questions on the number of models, but it is connected also to internal structure of the models. And then I gave you 3 steps of applications of classical applications now classical, of model theory in first order. First of all, decidability of the complex numbers, very classical. Then Axe quotient, less classical. And then Krzyzewski's proof that is, well, really much more contemporary. But now let us take a kind of a shift outside of first order logic. I just told you, a lot of important things in first order. Now, let us then consider this kind of duality. There is logical watching, where you watch through formulas, versus geometric acting. And we will see that this kind of metaphor that has been used by some people is a little bit what leads the current turn that I want to take around. So I take here a look at Ferrari's work. We're kind of entering a tangle like this. So there are some questions that one can query. We query structures. We ask questions to structures. Like in a Renaissance painting, we can ask, is there a tower behind the wall? Well, Renaissance perspective doesn't give you an answer to that. Or in a classical sonata, may you start your sonata in C major and resolve in D minor? Well, if it is classical, perhaps not. If it is not classical, then. But look how it depends on a system. Is time reversible in physics? If so, how? Well, this question is currently perhaps open for discussion in many different frameworks. But let me just say that in mathematics, we compare, we extend, we reduce, we stretch, we cut our structures. We do that all the time. And especially after mathematics in the 20th century started looking at many more structures, like Banach spaces or Lieb spaces for your differential equations or many other variants, we start doing these sort of operations to the structures all the time. And in model theory, we also have, well, it's also the mathematical theory that pushes these possibilities all the way. It is naturally anchored in logic, as we saw, in the possibility of querying structures. So logic gives you a way of asking questions in a language to the structures, in the implicit language they hold, but it also provides us ways of tracing the basic blocks. So to speak, the primary colors of structures. And later, like you give you a palette, you find the primary colors, and then you start blending in a controlled way. Like when you learn to blend colors, it later blends, combines all these blocks, helping produce all possible colors, all possible structures, but to produce them, not to have them as that random noise, but to learn how to produce them. Now, in recent years, even after model theory had honed its own logical anchoring to the point of providing that classification theory I just described, of all first-order theories and asymptotic dividing lines, that main gap, it started a kind of second sailing. I like that metaphor of second, like you sail a second time with all that you learned in the first time, toward a more geometric, algebraic approach, and apparently distancing itself from logic, which is strange. Model theory distances itself from logic, or maybe up to some point, we'll see. In 1975, Sharon Shelah wrote this paper, so this was early for him. This was just his 54th paper only, out of more than 1,000 now. The Lazy Model Theoretician's Guide to Stability. Well, we're still working on the consequences of this project that he deemed the Lazy Model Theoretician's Guide to Stability. So in 75, we have in mind mainly those who are interested in algebraically minded model theory. That is generic models, the class of existentially closed models and universal homogeneous models, rather than elementary classes and saturated models. Sorry, this is kind of in the bottom here, but anyway, it's kind of a very early description of a shift. We say, well, let us stop paying so much attention. It's not that elementary models given by theories are bad at all. They're very good, as he proved himself. But and many other people continue. But there are all perhaps some kind of different ways of doing model theory, and this started. So the results mentioned are now running deep at the heart of areas such as Galois theory for wide contexts, algebraic geometry. However, there are many reasons to try to extend the reach of logic and model theory beyond classes of structures axiomatizable in first order. Let me give you 3 different kinds of reasons. First of all, many natural classes of mathematical structures are in fact not axiomatizable in first order logic. They are out of the map that I gave you. So one could say, well, too bad. I mean, you're not in the map, too bad. Or maybe there is a way to extend the map, or maybe there is a way to transfer them in some way to the map. The second thing has been done many times by interpretation, and it works, but sometimes it may be, well, maybe the map has to be extended in some way. Many natural phenomena are not first order in nature. And even classes that may be captured in a first order way are sometimes better understood. And I think Boris Zilber will go much deeper in this line tomorrow, become tamer with stronger logics. A crucial example is Zilber's complex exponentiation. And sometimes, having a more general perspective may yield actually simpler proofs. Well, we are familiar with that. We know one has to be careful with this third aspect, but sometimes that happens. Some examples of the number one, not captured in first order, like Noetherian constructions, for instance, are not first order, locally finite groups, abelian groups, and their pure extensions and many variants, and elementary extensions of models of arithmetic and set theory. That's just a list of examples. Or they're not first order in nature. It's not that they're not captured, it's that they have a nature that is not really first order. Everything that has to do with convergence is not really well tuned to first order. So there you have analysis, Banach spaces, Hilbert spaces with operators acting on them, operator algebras of various kinds. So after I, gave so many good things to say for the map, I now say, well, it's missing important things. Or, yeah, as I said before, some structures might be better behaved if not analyzed with first order tools. Here I put the complex numbers with exponentiation, a very important situation in mathematics. And sometimes generality is good. Sometimes, as I will show in the end, we get some kind of clearer view by generality. This is, as I said before, always tricky. So now we go toward opening up the logic and go beyond first order. In the last, I guess, 15 minutes only that I have, I will try to describe a little bit which way this is going. Okay, so there are many, the many ways of shifting focus outward from first order have actually been there for a long time now. But isn't there the risk of losing grip? Now the focus will change to maybe stronger languages, infinitary languages, maybe stronger quantifiers, or maybe weaker languages. Sometimes this kind of goes toward computer science. You want weaker languages for good reasons, for resources reasons, or maybe no language. Yes, sometimes embedding between the models and closure properties in kind of a bypassing, not quite the language. There is always a language there, but bypassing the logic that is, and these are the so-called abstract elementary classes. By the way, tomorrow, Boris Zilber will also speak about abstract elementary classes. So, and then you can also embed convergence, continuity measures into the language. That's an analytic response. That's crucial in applications to Banach space theory and more recently to operator algebras. This is a different line. I won't go into that line today, but that's an important different line. Continuous model theory. Continuous model theory has been blossoming. It started in the 20th century very much, but it really exploded around the year 2000, and it is exploding in many different directions that happen. But I want to describe this change of focus from formulas to embeddings. So you replace formulas by looking at how one structure embeds into another structure, and you start wondering about amalgamation properties or maybe tameness properties of several sorts. So kind of a decent or indecent compromise is called abstract elementary classes. There is a language Tau. You want to describe a class of structures, but in principle, you don't want to focus on axiomatization, although you may do it if you want, and as we'll see, that happens also. But you focus on the way structures extend one another. Maybe the important part of this definition is to say that the classes will have two very strong construction features. You will be able to take unions of chains or unions of directed systems and not fall out of the class. And this is more technical, a Lowenham's column number for the class that enables you to look at smaller structures. So you can look at different structures. Instead of looking at which axioms they satisfy, you focus on how they extend one another, and you give regularity properties for these extensions and closure properties for the extensions. And these are the two main closure properties. Let me just give you a list of examples. So this extends first order. So first example is all classes that are axiomatizable by first order theories. But there are some metric versions of this that include Banach spaces, for instance, that I think it's important to mention that in the metric version of these classes. You can also take strange logics, infinitary logics, and take the classes axiomatized by those models, or you can take locally finite groups or what is called the Zilber class, the Zilber exponentiation class. There are many more examples, but let me just describe a little bit what is the correct notion of type, because I told you we need types in order to develop a stability theory. And types here are no longer sets of formulas because we are no longer focusing on formulas. So we take this idea of first build a large homogeneous model that there are several considerations that go into how one builds such a model in those abstract elementary classes, but in many cases it is possible to build. Just to give you an analogy, it's the analog of André Weil's universal model for algebraic geometry, but in the class. And then you say the Galois type of A and the Galois type of B are the same, if and only if there exists an homomorphism of the big structure fixing M and mapping A to E. So now the starting point for types is really orbits. You could do that as well in first order under some technicalities, but there it was equivalent to several different things. Here it is a version of our departing point. What is amazing is that this definition really is fruitful and extremely fruitful. It has generalized the classical notion of types, and it has really been able to extend part of the map that we had before, part of that map to abstract elementary classes. So we have a much larger map. We have some of those dividing lines, especially in the stable zone, inside the stable zone, that was that pink zone that I put in the picture. Let me just give you the picture very quickly. Yeah, in this picture. So now we have a much larger map, and so far the area that is quite well understood would be roughly the equivalent to the pink area. And it is quite amazing that one could do that with this new notion of types. That is something that is a little bit surprising if one thinks about it. So anyway, we were here in this picture of those types, right? And in the last minutes, we go to the last section I just described. So there is this new direction, no longer relying so much on logic. And there are 5 contemporary directions that I want to mention in this connection. So the first one was started by Scheller, and then Grossberg at Carnegie Mellon, and his set of students, Van Dieren and Boyn and Vasse, and it continues. But I mentioned these ones here. I have some pictures here. The first one is at Universidad Nacional in Bogotá, and the second one is in Suachoque, Colombia, where one of the proofs was discussed at one of the seminars we held in 2003, perhaps, I think, or 2000, yeah, perhaps 2003. So Scheller conjectured categoricity transfer for abstract elementary classes, connected to his, one of the aspects of the main gap. And there were early partial results with Mackay and Coleman from large cardinals. Grossberg starts working on this, and then, over the years, he built a whole group at Carnegie Mellon advancing this topic. Many students and many sophisticated results, kind of developing that stability theory. In 1999, so number 2 here is really the past 2 decades. With Scheller, so this is my introduction to the subject. We make the first steps towards superstability in abstract elementary classes. The first publication is from 1999. Van Dieren fixed issues in our work with Schellach, and she isolated, together with Rosberg, the notion of tameness that was kind of an important intermediate step. And then Boni, Vasse, Van Dieren, Grosberg developed stable AECs and many connections to categoricity. In parallel, Schellach developed frames and seriously, those were seriously improved by the Carnegie Mellon School. So a whole school was formed based mostly at Carnegie Mellon, dealing with that very specific line. A different thing. So Rzyszewski, who is now at Oxford, he was at the Hebrew University of Jerusalem since the 90s. Well, this is very recent work that might be connected with this line, and it is beginning to be connected. So this is a kind of very different direction. He isolated so-called patterns of definability. So you have definability again. One of the features that happen in first order as you go outside of the pink area, I noticed, is that types are no longer definable. And Rzyszewski, what he does is kind of building a structure that enables you to measure how undefinable they are. But by doing that, he gets a Galois theory of first order theories, one of the strongest generalizations of Galois theory available. And he has linked it to structural Ramsey theory to find the correct Galois object for a Galois correspondence for first order logic. That is a major work of 2020, roughly 2019. It's going on, but this has already been extended, mainly by Ori Segal in Jerusalem, but some other people, perhaps, a little bit beyond first order. And this is an interesting line because part of the approach is amenable to abstract elementary classes. I won't go into detail here, but something is happening there. Together with Schellach, we're now trying to find the internal logic of an abstract elementary class. So a little bit like if you take the map and now try to lift it, kind of finding a three-dimensional version of the map, which would be the version for abstract elementary classes. So getting axiomatization of an AEC, well, there was an early result by Schellach in the 1980s, but the prize was expanding the language. So that was, that one of the reasons that made possible all the development of abstract elementary classes was his presentation theorem. But we improved these results significantly in joint work from last year. Independently, there were some results by Leong at Carnegie Mellon. A sentence axiomatizes the abstract elementary class, and this offers new avenues to study definability of types, for instance, that is connected to the Rzyszewski question from the previous slide, and extending the stability map by a better syntactic control. So it's kind of the whole thing goes around. We went away from syntax, from logic. Now we're coming back, but it's a different logic, and we're trying to find it. There is a different line. So here's a photograph of Boris Zilber, whom you'll see tomorrow. He was visiting Bogota, I think, a few years ago. That's with two, one colleague and one student back then. So he started around 2001 to use axiomatization in infinitary logic of covers, the most famous complex exponentiation, to try to capture categorical versions of exponentiation and thereby study many classical conjectures, like Grothendieck conjectures and so on. Later on, with Harris, he extended this work to J invariants, and they linked model theoretic categoricity to a positive answer to a Serre conjecture on Tate modules that is linked to elliptic curves. And this has been extended to Shimura varieties. So you see, it's taking a very arithmetic flavor in his work. And why I mention it here, because it has to happen outside of first order logic, or it happens naturally outside of first order logic. There is a different direction here by Chernikov that is, I think, interesting. It is connected to ominimality. So ominimality has been very important, as I mentioned before, in first order, and it is still extremely important. And there are many different lines of avenues. So one of them is by Zilber, a version of ominimality adapted to abstract elementary classes. This is very current work by Zilber, and this may prove useful for real algebraic questions so far, eluding first order model theoretic treatment. And there is some interesting connection to higher category theory by Chernikov and Tausner. So they have embarked in trying to do stability theory for first order, but who knows where it will land. Stability may be recast as a question on recovering information about binary relations, given some abstraction from unary relations. That's a very weird way. I mean, we don't have the tools to say why binary versus unary, but the whole of that map that I showed, in a way, it's about interactions between 2 and 1. And Chernikov and Tausner have kind of taken up the question, well, let's now go up, like in category theory. And there are some interesting parallels, but this is also very deeply related to Schellach's theory of excellent classes from the 1980s, that is also important in abstract elementary classes. This is very theoretic, but it is connected to higher category theory in strange ways. So this is Chernikov's line. So this is my last slide, really, or next to last slide. It is just a map of perspectives. They put here at the center abstract elementary classes, and you have already seen all these, in the previous slides. I mentioned here the theory of modules by Masari Armida. Also, he was a student at Carnegie Mellon. He's now in Colorado, originally from UNAM in Mexico. And so you see, it's going also for model theory of modules. Masari Armida, Marcos Masari Armida, has been able to solve questions in modules by placing them in the correct abstract elementary classes. So this is a description of where it is going. My title was 21st century. Perhaps this, it was overly enthusiastic, but anyway. So thank you very much for your attention. Here I leave you with a quote by Simone Weil that I think is connected to these sort of questions that we were looking at today. Thank you. Gracias.
Thank you very much, Professor Villaveses. Does anyone have any question or comments? No? Again, thank you very much, Professor. Jessica, ¿quieres decir algo? Ok. Pues, excuse me.
Yeah, thank you
Bueno,
for your talk. And then we continue with the next talk. There is a question in the chat. Tatiana Berre asks, perhaps a strengthened axiomatic construction.
What do you mean? Yeah, well, strengthening, you mean the axiomatic construction of the classes, or sorry, what is the question? Because this may go in many different directions, of course, but you need to have also controls that will enable you to do all the internal, analysis of type definability, and at the same time control the sort of extensions that you want to get.
Perhaps make the axiomatic construction of geometry one of the
in a way, this has partially been done by something I didn't mention here, because in some way, part of what happens on one side of the dividing lines is that you do have a lot of a kind of geometric behavior. So inside one of the lines, what has happened is you have very few definable sets, and therefore they're amenable to do what are called combinatorial geometries, like matroids, pre-geometries. Those are what happened here. And also in abstract elementary classes, we have versions of that called quasi-minimal classes. So there are ways of kind of injecting geometry, but it's important to say that only happens at one corner of the map. It doesn't happen all over the place. And what happens outside of that corner of the map is really, you kind of start measuring how far you are from having this sort of a perfect situation that is kind of captured. So one of the reasons why O-minimality is so powerful is exactly that it has kind of this sort of a very geometrical flavor. It is connected to something called strong minimality, that is an even stronger version that really enables you to capture that sort of geometries.
Okay. Thank you very much.
Okay. Okay. Good morning, afternoon, or evening, everybody. I am Karina Navarro Gonzalez. I will allow myself to speak in Portuguese, but this little discourse will be translated, okay? Okay. Estou muito feliz de apresentar para todos vocês a professora Thaís Jordão. Thaís faz parte do corpo de professores do Instituto de Ciências Matemáticas e de Computação, ICMC, da Universidade de São Paulo, Brasil, onde ela é líder do grupo de pesquisa Análise Funcional Aplicada. Sua linha de pesquisa são o análise de Fourier, análise esférico e teoria da aproximação.
Okay. It makes me very happy to introduce Professor Thais Jordão to all of you. Thais is part of the department of the Institute of Mathematics and Computer Science, ICMAM, of the University of São Paulo, Brazil, where she is the leader of the Applied Functional Analysis Research Group. Her lines of research focus on Fourier analysis, spherical analysis, and approximation theory.
Desde seus começos como matemática, já demonstrava sua grande capacidade de pesquisa e divulgação. Obteve o prêmio Professor Carlos Teobaldo Gutierrez Vidalón por sua dissertação de mestrado em nível nacional e o prêmio da melhor defesa de doutorado apresentado no primeiro workshop de teses e dissertações em matemática na Universidade de São Paulo. Além de ter se formado como mestre e doutora nesta mesma universidade, ela também fez um pós-doutorado com estágio na Missouri State University, Estados Unidos, e um segundo pós-doutorado no Center for Mathematical Research, Espanha, ambos como bolsista da Fundação de Amparo à Pesquisa do Estado de São Paulo, FAPESP. Brasil, fundação de grande prestígio no país.
Since her beginnings as a mathematician, she has already demonstrated her great capacity for research and dissemination, obtaining the Professor Carlos Teobaldo Gutierrez Vidalón Award for her master thesis at the national level and the award for the best doctoral defense presented at the mathematical thesis and dissertation workshop at the University of São Paulo, Brazil. In addition to having training as a teacher and doctor at the same university, she also completed a postdoctoral fellowship at Missouri State University, MSU, United States, and a second postdoctoral fellowship at the Center of Mathematical Research, CRM, Spain, both as a foundation fellow. Support for research of the state of São Paulo, FAPESP, Brazil, a foundation of great prestige in the country.
Thaís não é apenas uma professora e pesquisadora apaixonada, ela também desempenha um papel fundamental na divulgação da ciência feita por mulheres. Criou, entre outros projetos, Ciência que Elas Fazem, onde o objetivo é trabalhar a igualdade e o equilíbrio de gênero dentro das ciências exatas. Um projeto que motiva as mulheres a permanecerem no meio científico, demonstrando que as mulheres podem gostar, sim, de matemática e podem ser tão capazes quanto os homens. Com toda essa entrega e sabedoria, orientar meus passos no doutorado. Thaís, amante de cachorrinhos e do crossfit, continua treinando intensamente na teoria de que a matemática pode ser divertida.
Thais is not only a passionate teacher and researcher, she also plays a fundamental role in the spreading of science made by women. She created a month of other projects, for example, Science That Women Do, where the purpose of is to work on equality and gender balance within the exact science, a project that motivated women to remain in the scientific environment, demonstrating women can be good in math as men. With all this dedication and wisdom, she has been guiding my way toward the doctorate. A CrossFit and puppy lover, Thais continued training hard on the theory that math can be fun.
Hoje, ela nos falará sobre a decadência transformada de Fourier e espaços de Vesov generalizados.
She will talk to us today about the decomposition of Fourier transformations and generalized visual space.
Pode começar, professora Thaís. Obrigada.
Teacher Thais.
Thank you very much. Are you listening okay?
Yes,
Yeah.
perfect.
Okay. I got a little bit emotional with this presentation. Okay, but thank you very much. Thank you, Karina, for remembering my achievements as a PhD student. It was very nice. Sometimes we forget those things, right? First of all, I would like to thank the invitation for this talk in ICMAM. And this event aiming to contribute to development of mathematics in Latin America and Caribbean. I would like to thank the organization, especially Karina, my PhD student, for the effort on providing a new space to spread the Latin American mathematics. Well, I need to share my screen. Just a minute. Can you help me to find the option desktop?
Okay, so can you share your screen? Do you have the option of sharing your screen?
I'm trying. 1 minute.
Okay. Wow, well, yes, we can see now your screen.
Full screen or just part of it?
Just the slides. We can see your slides.
Okay.
Okay.
So, I'm going to talk about new results about function spaces of generalized smoothness. Let me bring you here. Some applications of the decay of Fourier transform. I will present you new results, all to motivate the new results. And here the generalized smoothness space of functions, they will take the name of Bezout spaces. But generally speaking, spaces of generalized smoothness can be Lipschitz spaces or kind of fractional type of derivative spaces. These are the smoothness usual spaces. But I think I'll be clear about that through the talk. Well, the last 8 years since my PhD, I started studying generalized smoothness in order to improve results about the decay of Fourier coefficients for functions defined on the spherical settings, where we have all the harmonic analysis to construct Fourier series to talk about convergence of that, and to study the Fourier coefficients in order to derive good properties of the original function we are looking at the Fourier series expansion. The last 4 years, I have risked myself in studying the decay of Fourier transform, since it can be seen as an analog of the study, but on the Euclidean space instead the spherical setting. From bottom to top, the first paper brings a new technique. This was in my time in Missouri State University. This brings a new technique to obtain decay of the eigenvalue sequence of some integral operator defined on the sphere. In this framework, the Fourier coefficients, they are the same of the eigenvalue sequences in this paper. So this is kind of a result in aiming to study the asymptotic behavior of eigenvalue sequences. The second paper, this kind of study was made, but with a very general sort of smoothness condition. This was defined in terms of a family of multipliers operators, we can think that it is a family of average operators. And this helps us to measure smoothness of functions through measures of that. And then it helps us to define a general Holder conditions, since the usual ones normally are obtained about this one with very usual average operators. And in the last paper, these studies applied in order to study some numbers, approximation numbers, which are connected to what we call a metric entropy of some spaces of functions. On the Euclidean, actually, before to talk about the Euclidean space, I would like to point out that trying to reproduce what was made before, but for functions, smooth functions, smooth in the sense of derivative, joint with my PhD student, we find out that very important results in approximation theory relating approximation tools through asymptotic behavior too was missing in the literature to reproduce those results and improve them. Then we obtained some necessary equivalents. Those are papers mainly about approximation theory. And in 2021, we applied this equivalence between those tools in order to show that, it's possible to reproduce what we made before on a compact manifold, in a class of compact manifolds, including the n-dimensional spheres. In the Euclidean space, this concept of generalized smoothness was applied to improve results about the decay of Fourier transform. And in the middle of the way, since a new space was defined, some properties of them, motivated by, of course, another theories, were obtained in format of embeddings between these new generalized spaces. This is what I'm going to talk a little bit with you today. Okay, but before, I would like to note that generalized smoothness has been explored for many important mathematicians and different areas in mathematics. For example, the third paper, it can be seen that Bezoar spaces, those spaces of generalized smoothness, are used in order to obtain certain degree of regularity for solutions in differential equations. Then embeddings between those spaces are important in order to apply the natural process they use, inductive process. Nowadays, we have important mathematicians also working with that. For example, this paper from 2010, the author, Walter Trebels, he relates embeddings of the spaces of generalized smoothness with some very important inequalities in approximation theory. These inequalities are called Ulyanov type inequalities, and they answer very important questions made in the past for some approximation tools very used in the theory. Okay, and they imply classical embeddings as the classical Hartley-Littlewood in the last line, where it's possible to show that Lipschitz in the left hand right of this line formula is the usual Lipschitz spaces defined on the space of P-integral functions. And alpha and alpha minus gamma, they are the degree of smoothness given by the Lipschitz condition. It means the power of the function t to a power alpha, t to a power alpha minus gamma in the condition. And about the decay of the Fourier transform, we have what we call the basic decay. It's given for this inequality, the Pitts inequality. It says that if you look at the first formula in the left-hand side of inequality, it means that the Q norm, weighted Q norm of the Fourier transform, is smaller than the P norm of F. This smaller than is except for a constant here, which does not depend on the F variable. Yeah. So this Pitt inequality becomes Poincaré inequality for the right guess of index, Hartley-Littlewood inequality, and Hausdorff-Young inequality. And then if we add some Lipschitz condition, it's possible to improve the information about the decay of the Fourier. This result, due the Titchmarsh, called Titchmarsh theorem, it asserts that if square integral function satisfies Lipschitz condition, given here in blue. This Lipschitz condition is the following. In the integral, we have the difference operator acting on f. If we look at the integral, we have the L2 norm of this difference operator applied to f. And this condition means if it is big O of h to a power alpha, then the decay of the Fourier transform is big O of h to the same power. Actually, those conditions are equivalent. Several generalizations of the Titchmarsh theorem can be found in the literature, since generalizing the context for the Euclidean space, for manifolds, different manifolds, non-compact manifolds, but also generalizations in the sense that let's consider a weak type of Lipschitz condition, where with this condition, we can define a bigger space of smooth functions in this sense. So this is the path I followed. And to present to you a little bit about that, I need first to define those spaces to you, to convince you that they are nice generalizations of the basic ones. I would like to present some embeddings between them because they present a very, in the middle of the technique to prove the embeddings, the importance of some approximation theory tools. I forgot the word in English. Well, it's possible to make it clear that they are really important in the process to this study. And finally, I would like to show the Titchmarsh type theorem with those spaces where necessary sufficient conditions will be presented on the integral spaces of functions, not just for L2. L2 actually will be a corollary, and it will be the Titchmarsh theorem actually for the usual major function. So in the Titchmarsh theorem, in the right side of both conditions, we had the function h to a power alpha. We want to use in that place another function which helps us to measure smoothness, but we want to expand the possible of functions we can put in there and still have the theorem holding. So we will call measurement functions the candidates of functions to make this paper as the collection of functions from the positive real numbers to the positive real numbers, which are non-decreasing, measurable, going to zero as the variable goes to zero, and these last two, the condition 2, a technical condition. This condition means that if phi is the power function, then this power must be positive. So it seems a weird condition, but actually it makes all the sense because we don't want a bad behavior of this function near zero. Then collecting all the measurement functions, but now we consider a parameter beta positive, and then we define this class omega beta of the beta measurement functions. Let's call beta measurement functions. We collect the measurement functions satisfying now this integral inequality here. If we again look at the power function phi as being t to a power alpha, then this condition means that this power must be strictly smaller than beta. Then basically the power function is a beta measuring function if and only if the power is between 0 and beta strictly. Okay, the condition imposed to these beta measuring functions, this is equivalent of what we call the almost decreasingness property. This property means the following. Basically, you consider your phi over the power function. And we say that phi is almost decreasing if this quotient phi to a power, the specific power given the formula, is decreasing. And here note up to a constant again. A constant does not depend on t. This technical equivalence is very important because through it's possible to show, to exhibit a huge class of examples of beta measured functions. Because of course, I want to define a new space, I need to convince that this is a new, these have nice examples and important examples to the study and application of the concept in another areas. Okay, if we consider now the measurement functions, but for a parameter alpha, those measurement functions, I call this limit condition here as a homogeneous at infinite, homogeneous of degree alpha. If we consider those functions, then in this footnote book, it's treated about these regular variant functions. They can characterize them, and it's possible to show that all these regular variant functions are actually beta measurement functions, and then the characterization possible to the regular variant functions. We can now consider examples of measurement functions like this one in the second example. Power of t times a logarithm. We can also consider non-continuous functions.
Sorry, is just me or you lost your sound?
I lost the sound also.
Professor Jordao, we can't hear you.
I'm sorry, what?
Sorry, we lost your sound, your audio for some seconds.
Okay, but
okay,
it's
sorry.
back now.
It's
no,
very well
please
now.
interrupt me. I forgot to say, but any question, you can also interrupt me. Okay.
Okay, thank you. Now it's okay.
And any problem, Karina, please send me a WhatsApp message. I'm here. Okay. So this is an important information in the theory because extension of the Titchmarsh theorem were obtained for regularly variant functions. So if I want to improve this, I really need that this class of measuring function is strictly bigger than the previous one used to study the decay of the Fourier transform. Right. Now, the second step is to define the tool we use to measure the smoothness of the function. I would like also, again, to start from the bottom to top. If we consider R a positive parameter, this delta operator here is the difference of operator of order R, we call. This is defined as this summation, Here we have the binomial depending on this positive R. This number is defined in terms of the gamma function for R non a natural number. So this is well defined. And when R equals 1, this is exactly the operator, the Titchmarsh operator. Titchmarsh, the operator used in the Titchmarsh condition in his theorem. Okay. Now, using the difference operator, we define what we call the modulus of smoothness of order R on the integral space of functions. We define it taking the supremum on the Q norms of the difference operator. We don't need to look at the technical definition, but I want to present it. We just need to think that the modulus of smoothness, and it's used to measure smoothness, and the measuring functions are the power functions in the usual Lipschitz condition. We want to substitute to gain real general space of generalized smoothness. And then we are able to define them. Here, the parameter P means the space of integral functions I'm working on. And if we consider a beta majorant function, we define the Lipschitz spaces as being those functions such that the module of smoothness, the beta module of smoothness, is big O of the majorant function as t goes to 0. Hopefully speaking, all the usual classical Lipschitz conditions fits in this condition for the power function. If we add a second parameter, a Q parameter, and also between 1 and infinite, then we can consider what we call the Bezov spaces. Now, the Bezov spaces are the collection of those P-integral functions such that this quotient modulo of smoothness over the beta majorant functions under this weighted measure is finite. Those spaces are very nice because when Q is infinite, this space becomes the Lipschitz one, with the more general spaces than the Lipschitz one. But I'm going to talk mainly just the Lipschitz when I talk about the Titchmarsh theorem. Okay, so a little bit of properties of those spaces. First of all, if the beta majorant functions are the power functions, then these are what we call the usual Bezov spaces. And the natural, of course, question is, well, the usual one are embedded, can be embedded in the general ones. And the answer, yes, of course. We define it, we research a way to define those spaces in such a form. Some property must be fulfilled. The same for the Bezov spaces. If we consider the usual ones, they are always embedded in the general ones. But of course, we need to respect the degree of smoothness of the majorant functions in order to preserve the well definition of this space as the previous slide. Also, the second equality about this Lipschitz space is this is a nice equality because it means to us that the definition is good enough in the sense that the space depends just on the majorant function, not the modulo of smoothness employed, the degree of the modulo of smoothness employed to definition them. And it makes sense, of course, when we consider the usual Lipschitz space, hypothetically, they're not depending on the tool of smoothness, the measurement of smoothness we are using. I would like just not to give you a sketch of the proof, but the ideas included in the proof, because here resides the importance of the approximation theory in this approach. We can gain the equality before, just trying to show the classical, let's get one function, the space of the left right hand here, and let's show it's there, just making the condition true. But here, mainly what we need, except some not difficult calculation, is this relation between two different degrees of the same modulo of smoothness. This is a property that modulo of smoothness in general satisfies. This just means that the modulo of smoothness is non-decreasing in terms of the parameter of smoothness. And the second inequality, also relating different degrees of modulo of smoothness, is important in order to have the another inclusion from the right to the left. So in those inequalities are mainly researched and followed by researchers in approximation theory. This is a kind of relation my PhD student got in her PhDs do, but on the spherical setting. Okay, another classical or expected embedding between these new spaces are that the Lipschitz, they are stronger, they have stronger smoothness, well, they must be in the Bezov, right? This is true. Also that different degrees here in the last formula, we have two Bezov spaces. The embedding says that the parameter P, the P-integral functions where the space is defined, can be changed. We get the embedding. And also we have some hierarchy on the degree of smoothness here. This is a nice example. This generalizes the classical, what is true for the usual Bezov spaces. Well, and then for these embeddings and also for the important embeddings in the applications of the theory of Bezov spaces, then we need some new Ulyanov type inequalities, or it means new results relating different degrees of the same modulo of smoothness. We need those technical properties of the almost decreasedness of the measurement functions, because actually in this point, this is a trick condition which makes all the technique employed in the usual case be possible to generalize it for this context. And we apply the classical hard inequality in order to compare two different integrals, because we want to compare LP norms of Bezov quantities, and it involves double integrals. And usually for the power function, we apply the classical hard inequality, where we can upper bound a double integral. Here some order of the power functions appearing here. For the real important embeddings in terms of applications, we need, as I said, Ulyanov types. This is not a very beautiful slide in terms of calculations and inequalities, but the important here is to note that the results are new. It means that they didn't exist before 2010, 2021, here one. And those inequalities made possible to contribute in the sense of the decay of Fourier transform, as I will show you. And also, since we are working with measurement function, which are not power function, we need generalized versions of the Hardy inequality in order to compare double integrals with just one in the right-hand side inequality here. Also, they are huge inequalities. What's important here is the double integral, for example, in formula 4. We have a UT function here multiplying the integral from 0 to t. In the usual hard inequality, we have the power function. And this is a very important technical point also in order to do the several adaptations the theory needed in order to obtain the results. So with those tools available, we can show the same we showed for the Lipschitz space. They are well defined in the sense they're not depending on the degree of the moduli of smoothness employed to define the space. They just depend on the measuring function you use to define them. I'm just looking at the time. The second theorem asserts, this is a nice embedding for those studies. This is not my area, differential equations, but of course I have read about it because usually, of course, in mathematics, we just want to seek where the results want to prove are real important to others. This kind of application we mean in mathematics. Then this second theorem is important. This relates to Bezoff spaces. Now the target integral space is different. We have here a Q1 and a Q2, but also the order of smoothness phi, the measuring function phi, and our phi are important. But the problem of this theorem, it's nice, but the problem is that we need a technical condition about the measurement functions. But we can handle that if we straight a little bit the conditions on the parameters we use, the space of integral functions involved in the embedding. And in this version of this theorem, we have some conditions the parameter must fulfill, but the important is that we get similar embedding for some parameters, but without the condition on the asymptotic behavior of the quotient of the measuring functions involved in the embedding. And as a corollary, I think this is a very nice corollary. It's a beautiful because it presents a chain of Bezoff spaces. This chain means that I will mark in blue and I will reinterpret it simultaneously. This is a usual Bezoff spaces with degree gamma minus plus delta. This is in a generalized Bezoff space depending on a measurement function with degree equals to the usual. So the usual are in the general with the same degree. The general are embedded in all the usual with degree extremely smaller than where the measurement function before resides. And then we gain again that the usual is embedded in the general, that since we get the extremely smaller degree of smoothness, then we can put usual and general in usual and go on. So I think this is a nice chain to present. So these are the embeddings between the base of space, and here is the extension of the Titchmarsh theorem for these generalized smoothness spaces. Again, let's see what the result says essentially. If we are working on the space of P integral functions, but P between 1 and 2, here P prime means the conjugate exponent. So if we say that a function is Lipschitz, as defined here, then we have this equality including big O in the right-hand side of phi, our measurement function. In the left-hand side, we have the Q norm weighted, actually this is a weighted Q norm of the Fourier transform. And it means a lot about the decay of this transform. If now we consider the space of integral functions, but for P is smaller or equal to, and we know that the Fourier transform satisfies this condition big O, it means the Fourier transform decays like that, then we know that the original function is Lipschitz in the sense we have just defined. Well, we know that P equals 2, 1 and 2 hold. Then in this case, we have an if and only if. If is Lipschitz on the square two integral functions, the square integral functions, if and only if the Fourier transform decay like this big O of our measured function. And this is basically the Titchmarsh theorem for the Euclidean space. If we consider the dimension 1 and phi the power function, we have exactly the Titchmarsh theorem here. Okay. I will not extend myself talking about general monotonicity, but I just comment very, very rapidly that if we add some condition of our functions f combining smoothness with monotonicity conditions, then we can improve the result before, in the sense that we cannot improve necessarily the decay of the Fourier transform. We can slide the conditions in terms of have bigger intersection and result 1 and 2 in this slide. So that then we have an intersection for parameters where the Titchmarsh condition here are necessary is sufficient, or it means if and only if for this G5 theorem, not just for P equals 2. So this is the concept of general monotonicity. We just need to define it for real valuable functions defined on the positive real line. This is a technical condition defined recently in order to try to define a monotonicity in some sense on the Euclidean space. This is a very important topic when we work on radial functions on the Euclidean space. There is a vast area in harmonic analysis treating about those space of functions. So having this notion, it's possible to define them monotonicity on the Euclidean space. And basically, this is a technical condition which defines this. Of course, all this is motivated by by properties we need to be satisfied, since we look at the concept of monotonicity, usual concept monotonicity, starting with the usual, what we use, and decreasiness and increasiness, but it's a very modern way to bring this concept to functions on the Euclidean space. And important here is also a ugly set defined here, but if we consider this set the inverse of function, the inverse of Fourier transforms of functions, then we can improve the results before. The footnote means, the footnote brings the following. All the PD positive definite radial functions on the Euclidean space are in this space. So we can consider this corollary for those functions. If now we have a positive definite radial function, which is Lipschitz with Fourier transform non-negative, then we can get a punctual estimate for the Fourier transform. And this is Riemann-Lebesgue type inequality, we call the estimate, the punctual estimate for the Fourier transform. Of course, we have these estimates for the classical cases of Lipschitz space, but now these results allowed us to consider here, as I said, since the beginning, different functions of the power functions, even non-continuous functions to work with the decay of Fourier transform. So this is what I have prepared to you. I know maybe it was a little bit technical, but I wish that the main idea I could pass to you about this topic. Thank you.
Thank you very much. If you have questions, please raise your hand, virtual hand, and we will activate your microphone, okay? Does anyone have any questions or comments? Let me see.
In slide 18, there is in the chat.
Okay, so let me read the question. In slide 18, whether summation will be up to infinity or R. Someone is asking if in slide 18, the summation is up to infinity or just up
if
to R.
R is a natural number, this is finite, because from R, this binomial is 0. So R natural number, this is finite and goes to n, the natural number you choose. If R is not a natural number, this is an infinite summation. Okay.
Okay. Thank you. Other question?
Okay, maybe I have some questions or comment. Maybe let's wait if other people in the public, between the participants has questions, but I have some questions. Of course, this is a very nice talk. In the setting of harmonic analysis, you present this very interesting generalized best of spaces, and you did this Tishman characterization. Of course, this is valuable in harmonic analysis. My question is also in harmonic analysis, when I study, let's say, the boundedness of Fourier multipliers, of the Fourier transform. This kind of Marcinkiewicz conditions and Hormander-Milling conditions. If you have boundedness results in this direction for your best of spaces, this family of spaces that you introduce?
Well, this multiplier type theorem on the Euclidean space was applied in order to relate the approximation tools I said, the modulus of smoothness and the K-functional. The K-function, for those who know, this is a tool. It was first used in the interpolation theory, but this abstract thing, the module of smoothness is defined as a supremum, the K-function is defined as infimum. Those are very difficult to work with, and that's why we want to relate them somehow, because they are measurements of smoothness. Then for this equivalence, the multipliers theorem are very important. For the Euclidean space, this is work with one collaborator, Xinping Sun. We showed this equivalence. Mainly, we applied generalization of Marcinkiewicz theorem, because those multiplier, the difference operator and another's average operator, they are multipliers in that context. And then to compare the Q norm, we needed the multipliers. In the spherical setting, we also have versions of the Marcinkiewicz. Of course, the authors are very different, mainly from the approximation theory authors, and they are also essential to show the equivalences. Then through the equivalences between these tools, we can derive the embeddings for the base of spaces. I really don't know where these theorems can be applied in another studies involving the base of spaces.
Okay. Thank you. Maybe, let's see if other people between the participants have questions. I have other maybe, it's about if you have periodic versions of these base of spaces, of these generalized vector spaces, and periodic versions of your Teichmark theorem. Do you have this kind?
Periodic functions.
Yeah, like instead of the Fourier transform, Fourier series for functions between 0 to pi. Yes, I mean.
Yes. There are versions. I think it is in the path you were asking for the torus, right?
Okay.
Yeah, there are. The author is called Platonov. He has several versions of the Teichmark theorem for another context, but not so just change the emergent function, but the space, the initial space. So on the torus, yes, there exists.
Okay. I have other couple of questions, but maybe I will email you about this.
Yeah, that's why I didn't work on the Fourier series, because this results proof. But not for those emergent functions, but the proof is essentially the same. It's not a big contribution, because it's a very easy generalization for this class of functions, and consider the emergent functions, these emergent functions.
Okay. Okay. Any other question for our speaker? Okay, if not, so we can say thanks to Professor Thais Jordao for this very interesting talk.
Thank you for the questions. Unfortunately, I cannot see all of you. I wish I could, but thank you for the attention and for the invitation again. Very nice event.
Thanks to you to participate in this event.
Okay, so we have now one break. In Colombian time, we will return to the plenary talk of the conference, the first plenary talk, in charge of Professor Terence Tao. It will be in Colombian time at 11. So see you approximately in 1 hour. Thank you. Hello, Professor Tao. Oh, sorry, I have to make you co-host. So just.
Okay, hello.
Hello, Professor Tao. So, thank you very much for accepting our invitation.
Of course, no problem.
Okay, so if you want, we will start in 10 minutes, but if you want, we can check
Okay.
your slides.
Yeah. Let me. Okay, does that work?
Yes, it looks well. Maybe you can try to move your slides.
Okay.
Okay, it's okay. Yes. So now in UCLA new CL is time of teaching. You have teaching duties in this time?
Yes. Yeah, I teach on Monday, Wednesday, Friday. So today's a good day though.
Okay. So essentially this is a conference that we organized from Colombia for the Colombian Mathematical Society. And the idea was to invite maybe recognized people like you, maybe to inspire young mathematicians. So this format in Zoom is very well for this purpose.
Yeah. Okay. Unfortunately, I'm trying to figure out if I can draw on this. It doesn't really matter, but
yes,
there isn't a way to draw on this. It's a shame. Okay, well, I just have to use my slides, I guess.
Okay. So more or less the plan is that I will present you into one short speech, like 2 minutes. Then after you can start the plenary.
Okay.
The whiteboard.
Sorry?
Let me see. In the bottom, you have the option to choose the whiteboard. In the bottom, probably.
I mean, I can switch to a whiteboard.
You can switch
But when I go back to
the slides,
I don't seem to have an ability to draw. Normally, there's a option, but oh well. It's fine. I don't really need to write. It's not so important. Do you see my mouse? Like, if I move my mouse around, there's no. Like I'm moving my mouse around my name. There's no mouse visible.
It's visible, yes.
It is visible. You can
yes,
see it?
it's visible. Yes, it's perfect.
Okay.
It's
okay. So okay, I can just use my mouse. Okay.
So here maybe you see. Let me introduce some of the organizers.
Okay.
You can see Karina Navarro Gonzalez from Colombia. She's now in Sao Paulo.
Okay. Hello.
Hi, how are you?
Not bad. Not bad.
So here, other organizer, Jessica Gonzalez from Germany.
Okay, hello. So the entire conference is virtual. There is no physical meeting.
It's not a physical meeting. It's a virtual meeting. We created this conference 2 years ago. And then the idea was to continue with this in this format. Because
Okay,
especially this conference is running by young mathematicians and then from Colombia. So in future we want to organize maybe the conference in place, maybe with a major support. But until now we have this format.
Right. No, it makes sense. It's much cheaper to do it online.
Yes, maybe to apply for financial support sometimes is difficult, especially if one is in Latin America.
Right.
Okay, so let me wait just 2 minutes. How is the weather now?
Oh, it's nice. It's always nice here.
Yeah.
I mean, to the point where if it rains a little bit or it's just a little bit cold, then like it makes the news, and everyone is worried about the traffic and accidents.
I see.
Yeah.
Because now I am in Belgium and the weather changes very fast. So we pass from this very nice summer to this strong autumn. Have you been in Belgium before? Maybe with Bourgain?
Belgium, no, I guess not. I've been to the Netherlands several times, but didn't quite make it to Belgium.
Okay, maybe you are welcome. And in case you want to visit the Gen Analysis and PDL Center, you can visit us. Yes.
I had a graduate student from Belgium. He was very good. And of course, I know Jean and Ingrid Dawishis too. I guess I've never been to Belgium. No.
Okay, Stein also, yes, is from Belgium.
Professor right,
Stein.
Yeah, he left when he was very, very young.
Yes.
Yeah.
Okay, also we have with us other of our plenary speakers, Professor Kenny. No.
Okay. Hi, Carlos. We can't unmute. So.
Yes. Now Professor Kenny can unmute at himself if he wants. Okay, so maybe we can start. So, okay, I will give a couple of words in Spanish, and then I will present to Professor Tao in English. So, muchas gracias. So, buenos días a todos. Es mi gran placer introducir a una de las mentes más brillantes de nuestro tiempo, el profesor Terence Tao, desde la Universidad de California, Los Ángeles. Por motivo de nuestra globalizada participación con más de 40 países en esta ocasión, le introduciré en inglés el lenguaje en el cual él nos transmitirá su charla. So, ladies and gentlemen, good morning and welcome to our first plenary. We have with us one of the most eminent and brilliant minds ever, Professor Terence Tao. His very well-known mathematical career is connected with giant antecessors in the field. He did his PhD at Princeton University under the supervision of Eli Stein, a big name of Chicago's Harmonic Analysis School. the one that connects Latin America and the USA in view of the historical cooperation between Alberto Calderon and Anthony ICMAM. Professor Tao was born in Adelaide, Australia. He discovered his passion for mathematics as a child while playing games and solving puzzles. At 13, he became the youngest winner of the International Mathematical Olympiad. He came to the USA when he was 16 to pursue a PhD at Princeton, and 8 years later, he was appointed a full professor in the departments of mathematics at the University of California, Los Angeles, making him the youngest tenured professor at UCL. In 2006, Professor Tao was awarded the Fields Medal, considered the Nobel Prize of Mathematics, for his contributions to partial differential equations, combinatorics, harmonic analysis, and additive number theory. His other awards include the MacArthur Fellowship, the Breakthrough Prize in Math, and many others. Between the contributions of Professor Tao to mathematics, one can mention, in PDE, his work until 2010, where he was part of the well-known collaboration with James Colliander, Marcus Gill, Gigliola Stafilani, and Hideo Takaoka. They found a number of novel results, many to do with the well-posedness of weak solutions for Schrödinger equations, KdV equations, and KdV-type equations. With Michael Christ and Colliander, Professor Tao developed methods of Koenig, Ponce, and Vega to establish ill-posedness of certain Schrödinger and KdV equations. In harmonic analysis, Professor Tao resolved the Fluget conjecture in the negative for dimensions larger than 5, based in the construction of an elementary counterexample to an analogous problem in the setting of finite groups. With Camille Muscalu and Christoph Thiel, he considered certain multilinear singular integral operators with the multipliers allowed to degenerate on an hyperplane, identify conditions which ensure the operator continuity relative to LP spaces. This unified and sent earlier notable results by Koifman, Koenig, Lacey, Meyer, and Stein. Extensions of these estimates were used in establishing well-posedness results for dispersive partial differential equations, following famous earlier works by Bourgain, Ponce, and Vega, among others. A number of Tao's results deal with restriction phenomena in Fourier analysis, which have been widely studied since seminal articles of Charles Pfefferman, Robert Strickers, and Peter Thomas in the 70s. His results in analytic number theory and arithmetic combinatorics, together with Jane Bourgain and Ned Katz, are very remarkable. In number theory, together with the University of Oxford professor Ben Green, Professor Tao proved the Green-Tao theorem, which states that there are arbitrarily long arithmetic progressions of primes. His passion for mathematics, discipline, and humanity makes him a model to follow for our future Latin American generations. I can testify his work will occupy an important place in the history of mathematics. So thank you very much, Professor Tao, and please continue with your plenary.
Okay, thank you very much. Muchas gracias. Okay, yeah, it's a great pleasure to be here virtually in this very nice conference here. So I'm going to talk about a very speculative thing I've been working on the last few years to try to understand these very difficult fluid equations and hopefully one day to actually create blow-up solutions for these equations. It's not nowhere near completed yet, this program, but I still think it is possible to make this work. So so I'll be focusing on two fluid equations that are quite well known. One is the Navier-Stokes equations, and these are the equations that model an incompressible fluid with viscosity. So the unknowns are a velocity field u, which for any time and any position is a vector in 3 dimensions, and it obeys a certain equation. It is transported by itself, it flows, and it also dissipates by some viscosity. So nu is just some positive constant. It measures the viscosity of the fluid, and there's also a pressure term which is coming from the incompressibility of the fluid. And we also require that, again, because of the incompressibility, that the divergence of U is always 0. So this models, for example, fluids like water, which are pretty much incompressible and have a little bit of viscosity. There's a limit when you send the viscosity to 0, that's called the Euler equations. And that's the limiting case of the Navier-Stokes equations. Here I've defined these fluid equations in 3 dimensions, R3, because that's the world we live in. But mathematically, you could consider these equations on other domains. You could put a boundary, or you could work on an arbitrary smooth manifold. You just have to replace like Laplacian with things like the Laplace-Beltrami operator to make some other natural geometric modifications, which I won't specify here. Okay, for these equations, people study both smooth solutions, or also called classical solutions, where all the functions are very, very nice, very smooth, and decay at some suitable rate at infinity. But they also study weak solutions, where you only have a limited amount of regularity. These are both important, but in this talk, I will only talk about strong solutions. I will not talk about weak solutions very much. If you assume smooth solutions, then you can simplify the system of equations. So U is divergence-free. So that means that the time derivative is also divergence-free. This Laplacian is divergence-free. And this gradient is orthogonal to divergence-free vector fields. That's a simple integration by parts. So you can project, there's something called the Leray projection. There's an orthogonal projection. You can project any vector field to a divergence-free vector field. And there's a projection operator called the Leray projection, which is called P. It's a singular integral. And if you apply this projection, you can simplify the system of 2 equations into a single equation, basically a heat equation. The time derivative of U is actually just viscosity times Laplacian U plus a nonlinear expression, BUU. And B is sometimes called the Euler operator. It is basically the projection of U dot grad U. So you differentiate U in the direction U, or if you have BUV, you differentiate U in the direction of V and V in the direction of U, take the average, and that's some funny nonlinear operator called BUU. So you can think of the Navier-Stokes equation as a semi-linear heat equation. So the heat equation with a nonlinearity. Now this BUU, this nonlinear operator is not completely arbitrary. It obeys some properties. So one of them is that it obeys a certain cancellation law. So BUU is the effect of transport. It's the fact that fluids are actually moved. The velocity field actually moves the fluid around. But it always moves, because of incompressibility, it moves the fluid around in a direction which is always orthogonal to U. If you take the L2 inner product of BUU with U, you always get 0. That's an integration of parts identity that you can check. And as a consequence, this nonlinear heat equation, it can never increase the L2 norm of your solution. So the L2 norm of solution is called the energy. It's basically the kinetic energy up to a constant. And so for smooth solutions, you get what's called the energy identity, that the energy of your solution at time t is less than the energy of the solution at time 0, and the amount of energy dissipation is given by the viscosity times the integral of the gradient. So the viscosity is slowly draining energy from the fluid. So as the fluid keeps evolving, it becomes less and less energetic, and eventually you expect it to calm down and become 0. Which is what you see in practice. If you splash water around, it may be chaotic for a while, but eventually it settles down and becomes calm. Okay, so what do we know about this equation? So for these sort of time evolution equations, the natural question is the initial value problem. That if you specify an initial velocity, now it has to obey one compatibility condition. It has to be divergence-free because of the incompressibility. But if you specify any nice initial velocity, so smooth and well-behaved, has to decay at infinity. I won't specify exactly what that means. It's just a technicality. But if you can give me initial data, then you can solve the equation up to some time. So there is some maximal time of existence, which I call T star. And you can solve you can find a unique smooth solution U, which has some decay infinity, which you can solve for the velocity field and also the pressure field P. It's a type will actually be a scalar, not a vector field. So for either for Navier-Stokes or Euler, they both have what's called local well posedness, that you can solve both these equations up to some time T star. So you can solve for some positive time, and then something happens. So one or two things happen. Either the good case is you have a global regularity, that the solutions exist for all time. Or you have what's called finite time blowout, that the solution only exists for a finite time. And furthermore, as you approach the finite time, the solution becomes more and more badly behaved. For example, if you take the infinity, the sup norm of the velocity, it will diverge. And I stated this for R3, but this local existence theorem is true in any dimension and on any manifold. Now, these equations are supposed to model fluids, and of course, when fluids do not blow up, right? You splash some water around, it will not explode. It will keep existing. But mathematically, it's possible, theoretically, that the Navier-Stokes or Euler equations actually do develop finite time blow up. This will not necessarily mean that that real-life fluids blow up. What it means is that the Navier-Stokes or Euler equations will stop being a good approximation to the fluid. So real-life fluids, they don't exactly solve Navier-Stokes or Euler. They solve a much more complicated equation, maybe Boltzmann or a kinetic equation. But we believe that these are good approximations, and when we do predictions of, say, ocean currents and so forth, they do seem to be fairly good approximations, at least for short time periods, like a few days. But if there's blow up, that means that these equations stop being physically good models for actual physical fluids. And there's a major famous question whether finite time blow up is possible either for Navier-Stokes or Euler. And we don't know. And in fact, with Navier-Stokes, it's one of the Clay Millennium Prize problems, one of these $1 million problems to prove or disprove whether finite time blow up is known, or it can happen or not. And that's still open. Now, for all these equations, for many types of PDE, there are these scaling heuristics that, or dimensional analysis heuristics that you can use to make a prediction as to whether this blow up can occur or not. And unfortunately, in this case, it's inconclusive. It says that blow up might happen, but maybe it doesn't. It is not very satisfactory. So let me explain these heuristics. Okay, so let's take Navier-Stokes, and to simplify, let's normalize the viscosity to be 1. And there's a simple scaling you can use to do that. So to simplify things, we make the following ansatz. We suppose that at every time t, the fluid, U, is mostly exhibits a certain frequency. So it has a certain frequency, n, which depends on time. Or in other words, it oscillates at some wavelength, and the wavelength is the reciprocal of the frequency. So the fluid has some natural length scale, 1 over n, and has some amplitude a. So the amplitude is like the average speed. So at any given time, we assume that the fluid is doing something at a certain wavelength, at a certain frequency, and a certain amplitude. And if you make that heuristic, then you can start estimating the size of various terms. So the viscosity term, so that's the term that's trying to make the fluid calm down and become constant and 0. U is of size of the amplitude. Every time you differentiate, that's like multiplying by the frequency. So taking Laplacian, that's 2 derivatives, that's like multiplying by 2 copies of the frequency. So that should be about n squared a. And the viscosity we have normalized to be 1. So the viscosity term is about n squared a. But this bilinear term, this nonlinear term, which is coming from transport, so that's a term that could potentially create shocks or some other really bad behavior. This is the term that could cause blow up. So that's a projection of U grad U. U is of size a, gradient adds a factor of n, and the projection is bounded. So heuristically, this type of expression should look like a times n, so n times a squared. So this is the nonlinear term, and this is the linear term. And so they have different sizes, and which one dominates depends on which is bigger, the frequency or the amplitude. So if the frequency is bigger than the amplitude, the viscosity term dominates, and if the amplitude is bigger than the frequency, the nonlinear term dominates. So I'm just repeating that. When the amplitude is low or frequency is high, we expect viscosity effects to dominate, so then the equation behaves like the heat equation, and so you should have global regularity in this case. But nonlinear effects, transport, should dominate when you have high amplitude, when the amplitude is higher than the frequency. So if you want to blow up, you want the amplitude to be higher than the frequency. So you can make a power law model. Maybe the frequency is going to infinity, so the solution is becoming more and more high frequency. So the wavelengths are becoming smaller and smaller, which is what you see when you have turbulence. And you can assume some sort of power law that maybe as the solution gets more and more turbulent, the amplitude gets increases by a power law to some exponent theta, which is bigger than 1, so that the viscosity effects are dominated by the nonlinear effects. And if you plug this power law into the Navier-Stokes equations, you will find that the frequency should start increasing or that the frequency should fluctuate at a rate which is a positive power, or bigger than 1, of the frequency itself. And this is an ODE which could blow up in finite time. So heuristically, this kind of power law could lead to blow up. But the question is, can this power law actually happen? So for which exponents theta can this power law happen? Well, the one thing we know about fluids, about the Navier-Stokes equations, is the energy conservation. So you can start computing the energy, but we need one extra number to predict what the energy is like. So sometimes we expect the fluid to be intermittent, so that as you approach some sort of blow up, maybe the solution is concentrating on not in a 3-dimensional set, but maybe on some smaller dimensional set, that the energy is concentrating maybe at a point or a line or a fractal. So let's assume that that the time is beginning at any given time, the solution is concentrating at some intermediate set of some dimension alpha, somewhere between 0 and 3. So it could concentrate all the way to a point, it's an alpha 0, or it could be spreading out all over space, so alpha is 3, or maybe something in between. So given that we know the wavelength is 1 over n, so this, at any time t, the solution would be supported in a 1 over n neighborhood of an alpha dimensional set. So the volume heuristically should be something like n to the minus 3 plus alpha. So for example, if alpha is 3, it should be supported on a unit volume set. If you're concentrated at a point, then you should be supported on a little ball of size 1 over n, which is volume n to the minus 3. So now you know this volume, you can compute the energy. The energy is the integral over all the space, u squared. So that's amplitude squared times the volume that the solution lives in. So that's this expression here. So that's n to a certain power. So if you want to have blow up, you need the energy to stay bounded. So you need this exponent to stay negative. So if you work out what that means that the power law, the rate of growth of amplitude, is bounded above by 3/2 minus alpha over 2. Okay, so there's an upper limit as to how much the amplitude can grow. Okay, so in order to blow up, we want alpha to theta, the blow up rate has to be bigger than 1, but less than this number here. So so that is possible, but only when you have a very intermittent solution. So that means that the dimension in which you concentrate has to be less than 1. Okay, so you can't. So this tells you that blow up might be possible for Navier-Stokes, but only if you concentrate in a set of dimension less than 1. And in fact, there's a rigorous result of that. It's a famous result of Caffarelli, Kohn, and Nuremberg. So this also tells us that if you want the most extreme example blow up, you want to blow up as fast as possible, theta as big as possible. The largest blow up rate is theta equals 3/2, and that would occur when alpha is 0. So the most extreme blow up is when the fluid is somehow compressing all the energy into a single point. Of course, the fluid is not compressing to a point because the fluid is incompressible, but maybe the fluid is somehow transferring its energy into smaller and smaller balls. So the most dramatic blow-up scenario that is consistent with all our heuristics is a single point concentration, sometimes known as a type 1 concentration. No, it's not. Okay, it's not type 1, but it's concentration at a point where at any given time you're supported in a single ball of radius equal to the wavelength. So you're concentrated in a little ball of size 1 over n, and the amplitude is as large as possible while still having bounded energy, which is about n to the 3/2. And right now, with our current technology, cannot exclude the possibility that this blow up, that this concentration occurs, and that this frequency is going to infinity. So this ball is shrinking to 0, and the amplitude is going to infinity as you approach some finite blow up time. So this is the most extreme blow up scenario that we cannot currently exclude. So this is what dimensional analysis tells us. It tells us that maybe a scenario like this is possible, but it all depends on this nonlinearity, whether this nonlinearity acts to keep increasing the frequency, or maybe it keeps the frequency about constant or decreases it. Now, to analyze this situation, the full fluid equations are hard. So people often study simpler models of these equations. Maybe they add symmetry assumptions or they do approximations. One particularly simple model that turns the PDE into an ODE is what's called a dyadic shell model. So we assume that at any given time, the amplitude is just given by, the solution is given by maybe a single wavelet multiplied by an amplitude, which I've renormalized to call x. So at every single frequency scale, you just have one scalar that measures how much amplitude or energy you have at a given scale. So you can do some heuristics, and you can decompose frequency into various dyadic shells. You pick some constant lambda bigger than 1, say 2, and you take some dyadic ranges of frequencies like lambda to a certain power for different n's, and for each n you calculate how much amplitude you have at a certain scale. You normalize it, and you make some assumptions, and you can arrive at a certain equation where at any given frequency scale, the rate of change of amplitude or normalized amplitude at a certain scale is influenced by nonlinear effects from nearby frequencies. So the frequency at a frequency range n, the frequency is at range n-1 or n+1 can influence so there can be energy transfer between adjacent frequency scales, but there's also dissipation. So the viscosity becomes just a damping equation. So if you didn't have the nonlinear terms, this would just decay at some exponential rate. And the higher n, the higher frequency you have, the more the larger this is, the more damping you have. So this is dissipation, and then you have some energy transfer. So this is a simplified model, which was introduced actually back in the 70s and then popularized by Katlin Pavlovich in the 2000s. And this is normalized, so the total energy is actually, in this case, just the sum of the squares of these coefficients. These are scalar quantities. So this is a toy model, which is quite easy to analyze. You can even solve it on a computer numerically. The blow-up scenario that we discussed before, where all this energy is concentrated at a point, what that corresponds to in this toy model is if all the energy at any given time is concentrated in one mode. So there's a single, anytime there's a single n where almost all the energy is sitting. And then as time moves by, as time goes on, the energy moves to a higher and higher frequency, and it does so faster and faster. And so by a finite time, the energy has moved all the way to infinity, and you get a blow-up. The larger you make n, the less important this viscosity term is. You see, if you go back, you can see that there's a lambda to the 4/5 here, but here you have a lambda to the n. That as long as the x's are of size about 1, the nonlinear effects will dominate the viscosity effects as long as you have high amplitude. Okay, and if you modify the equation a little bit, if you replace this 4/5 with something below 2/3, it actually was shown by Cheskudov that actually this toy equation does actually blow up. So going below 2/3 corresponds to going to 5 and higher dimensions. So this analysis suggests that at least in 5 and higher dimensions, Navier-Stokes could blow up. But this is not conclusive because this is only a model equation. This is not the actual Navier-Stokes equation. But unfortunately, or fortunately, depending on your point of view, some people believe in global regularity, some believe in blow-up. I believe in blow-up personally. But in 2011, Barbato, Morandin, and Romito analyzed this equation in 3 dimensions and actually showed that, assuming some initial condition hypothesis, I think positivity, that actually you had global existence, that the solutions actually did exist globally for all time, and the energy did not escape to infinity. And roughly speaking, the reason is that as the time evolves, the solution does spread a little bit. It does move the energy a little bit to high frequencies, but when it does so, it spreads out the energy among many, many modes. So there's no one mode that captures all the energy. It's all spread out to be low amplitude in many different energy modes at the same time, frequency modes at the same time. And because of that, the viscosity has a chance to dominate the nonlinear effects, because now you have low amplitude, and the viscosity ends up damping out the solution. So there's enough spread that viscosity wins. So if you want to have blow up, if you want to outrun viscosity, you have to stop the solution from diffusing into multiple frequencies. You have to keep it all contained in a single frequency mode. So I got interested in this problem many years ago, and even though this particular dyadic shell model had this diffusion that allowed the solutions to spread out, it's possible to modify the dyadic shell model in which the dynamics, you can encode kind of a barrier, a time delay. So you can make it so that the solution concentrates at one mode, and then it stops. It waits for a bit, and then until all the energy from the previous mode has sort of accumulated at this one mode. And then when it's ready, another part of the dynamics opens up, and then suddenly all the energy flows from one mode to the next mode. So there's this gate that opens very suddenly, and then energy rushes into the next mode, and then it stops. It waits for all the energy to catch up, and then you open up the next channel, and then it moves again. So there's a stop, start nature to the dynamics. And if you set that up properly, then you can keep the solution coherent in frequency, and it doesn't get affected by viscosity too much. So this was a complicated model. I will flash it on the next slide just to show how complicated it is. On the fluid side, what it corresponds to is that it corresponds to replacing the Navier-Stokes equations by what I call an average Navier-Stokes equation, where you replace the effect of transport by this B, you replace by an average version of B, like sort of where you turn off certain interactions and you only keep a small number of interactions that actually do what I wanted it to do. It still obeys the energy identity, and this equation still obeys many of the properties that Navier-Stokes does. But what this analysis shows is that this equation does exhibit finite time blow up pretty much of this type, where theta of the maximal rate of theta over 3/2, and concentration intermittence, minimal intermittency or maximal intermittency, concentrating at a single point. Now, so the actual equations are quite complicated, and they involve two parameters, epsilon and k. Okay, but so I needed, instead of one scalar at every scale, I needed four scalars at every scale to control these gates that are opening and closing. But I had this little diagram to explain. I was actually motivated because my wife was an electrical engineer, and electrical engineers have all these diagrams to model ODEs by these circuits. And it was very helpful actually to use these diagrams. So at every scale, there are these four modes that are interacting with each other, and then there's this gate that moves every four modes to the next scale. But you have to set it up so that the gate takes a certain amount of time to open, and then once it opens, it floods through. But anyway, I won't discuss this diagram much further here. Okay, so that was a rather complicated analysis. But so what are the lessons that one draws from this? So it tells you that, first of all, that so this model conserves energy. So energy conservation is not strong enough to prevent this type of blow-up scenario, because there are equations very similar to the Navier-Stokes equations analytically that do blow up. So there are many attempts to solve to try to prove global regularity for Navier-Stokes. I get, in fact, many manuscripts every so often about this, and many of them, they say, okay, we're just going to try controlling the energy and using Sobolev embedding and so forth. And basically, we know now that no attempt, unless you introduce a really special, unless you really exploit a property that only the Navier-Stokes equations have and is not shared by these other models, you cannot prevent blow-up just by sort of standard techniques, because most of these techniques also apply to all these other equations. But if you do blow up this quickly, the viscosity effects are negligible, and really blow up for this in this scenario is almost the same as blow up for Euler. And the type of blow up should be some sort of approximately self-similar blow up, so that your solution should exist at some scale at one time, and then at a later time it will contract to a smaller version of itself, maybe with some residual energy left over, and then it will contract again to after some discrete time, maybe. So it will wait, and then it will contract, and then it will stop, wait, and it will contract. So it should have some sort of discretely, approximately self-similar behavior. That should be the type of blow-up scenario that could potentially contradict global regularity. It can only be discretely self-similar. There are results showing that continuous self-similar solutions cannot exist, assuming that there's enough decay infinity. Okay, and as I said, you have to somehow program a time delay. So your solution can't just mindlessly push all its energy to higher and higher frequencies, and that will create leakage and all kinds of problems. You have to program some sort of delay every time. It's like trying to go through a dam or the Panama Canal, where you have to keep open. You have to wait until a certain gate opens before you can move your ship through. And you need to choose very careful initial data. The type of blowups that we construct here actually are very unstable. If you change the initial data a little bit, the blowup can fall apart. Okay, so all right. So in this scenario, viscosity is negligible. So really, the question is really about the Euler equations. Can you make the Euler equations blow up at this very extreme rate where the fluid is concentrating at a single point? Now, recently there's been a lot of exciting progress in constructing blow-up solutions to Euler at low regularity. For example, there's this work of Tarek El-Guindi, that creates blow-up at a certain, which is moderately regular, C1 alpha. But for the classical problem, we actually need solutions that are smooth, and the El-Guindi construction, unfortunately, relies very much on having a very mild singularity at one point. There's also examples of blow up using vortex patches and also by exploiting boundary effects. In fact, very recently, this is very nice work of Hu and Liu, I think, where they actually get blow up for Euler, actually symmetric Euler with a boundary. But in the absence of a boundary, we don't yet have any blow up results. One reason why things are harder is it's harder to construct blow-up for Euler because the Euler equations have more conservation laws than Navier-Stokes. Navier-Stokes conserves energy and one or two other quantities, but the Euler equations conserve many more quantities. They conserve something called circulation. So this is Kelvin's law of circulation, that if you take a loop in space and you integrate the velocity on that loop, or equivalently by Stokes' theorem, if you integrate the curl of the velocity called the vorticity on any surface that spans the loop, that quantity is preserved by the flow. And in fact, there's a way to write the Euler equations. There's something called the vorticity stream formulation of the Euler equations. The Euler equations you can write in terms of vorticity, which is the curl of the velocity, and the curl gets transported by the flow by the lead derivative, in fact, and the velocity is recovered from the vorticity by a certain integral operator called the Biot-Savart law. So this is another form of the Euler equations. And similarly to what I did for Navier-Stokes, I showed that the Euler equations also exhibit blow-up. But you have to cheat. If you modify the Biot-Savart law to another variant of the Biot-Savart law, which obeys very similar estimates, but you keep the transport equation. So and this transport equation is what gives you conservation of energy and conservation of circulation and most of the other conservation laws. Then these equations still can exhibit finite time blow-up. So even circulation conservation and energy conservation are not enough to prevent blow-up. So I don't have time to. Okay, so maybe I'll skip a little bit the construction, but I'll just show you the picture. The picture is a vortex neck pinch. So the fluid is actually spinning around like a whirlpool, and there are these vortex lines that it is spinning on. If you take the curl, the vorticity actually is moving in this direction, and I choose the Biot-Savart law to keep pinching the fluid at a certain neck so that it keeps moving. This neck keeps shrinking to a point, and as time approaches 1, the width of this neck actually approaches 0, and so you can get blow up. Unfortunately, I could not get the theta equals 3/2 blow up. I could only get theta equals 1 by this construction, which is a bit annoying because that's not enough to lead to Navier-Stokes type blow up. But it does show at least that blow up is potentially possible for these Euler type equations. And this is purely theoretical, but it is nice to remark that people have actually done numerical simulations of the actual Euler equations for these kind of vortex tubes. And in fact, based on inspired by a suggestion I made in one of these papers, this group of authors studied actually pairs of vortex tubes, so like two little spirals of fluid. And they did notice that actually, so they interact with each other. If they move in opposite directions, they attract each other, and they can curl up in a very complicated way. but in a way that they become thinner and thinner and closer. And so it is somewhat consistent with this pinching type scenario that I was able to get for this model equation. But they could only run this kind of pinching effect. They could run for about 2 scales before their numerics stopped working. But still, there was this sort of entanglement type scenario, which is tantalizing evidence maybe that this kind of scenario could actually happen for the actual equations. So anyway, but those are very artificial equations. I had to artificially change the Biot-Savart to something, to a very carefully designed operator, which is not geometric. But it would be really nice if we could actually find a geometric version of the Euler equations that did actually blow up. So what I conjecture is that there should be some manifold, maybe of high dimension, but it's a smooth manifold without boundary, and some smooth solutions, the Euler equations on that manifold, which blows up. And based on what I was able to do before, one way to try to attack this conjecture is to be able to program things like delays. Like you want to be able to, maybe by choosing the metric very carefully, be able to design solutions that stay at one scale at some time and then suddenly move to another scale and then stop and then move to another scale. So you want to program some complicated behavior into your solution. So my hope was to use the ability to change the metric to create what's called universality in the computer science sense, that you should be able to model almost any Turing machine actually by an Euler flow. So there are some other ODEs and PDEs that are known to be Turing complete. That for any Turing machine, you can find some initial data for this ODE or PDE, which will develop singularities if and only if the Turing machine holds or doesn't hold, or something like that. So people do study the complexity of PDEs. And so my belief is that the Euler equations are so complicated that you can model arbitrary Turing machines. And once you can model Turing machines, maybe you can program, you can force them to blow up. So I started working on this a few years ago. So one thing I showed is that these Euler equations are complicated enough to at least model all quadratic equations. So any ODE of the form dtu equals some bilinear function of u, where u now takes values in a finite dimensional vector space, in a product space actually, and B has to obey the energy condition. BUU has to be orthogonal to u, just like it is for Euler. Any such ODE can be embedded into one of the Euler equations. So for any such ODE, there is a manifold, compact smooth manifold, and some way of embedding your vector space into smooth flows on that manifold, so that the dynamics of the Euler equation restrict on that subspace to this quadratic ODE. So every quadratic ODE can actually show up as a special case of one of the Euler equations. So this is by a direct construction. I had to actually work on a certain Lie group across the torus, and I just write down a metric. So basically, any quadratic ODE that obeys a conservation law can also be converted into a solution of the Euler equations. So if one of these ODEs had finite time blow up, this would imply that Euler had finite time blow up. Unfortunately, for ODEs, any ODE that has a conservation law does not blow up. That's a consequence of the Picard existence theorem. So this doesn't directly create blow up, but it does give some hint towards universality. Another thing I was able to show a little bit later was that instead of all, so an Euler flow creates an incompressible flow on a manifold. And in fact, every incompressible flow on a manifold, well, not every flow, but many flows actually come from Euler flows. There's a somewhere that, in the sense of category, that the set of flows that can be approximated by an Euler flow in a certain technical sense it's not the entire set. It actually is meager, but it is dense somewhere in the smooth topology. So there's a large set of flows that can be approximated. So in particular, this means that there are flows that are chaotic. There are flows with positive entropy and so forth. Okay, so although there's one catch, if you want to approximate a general flow by an Euler flow, you have to use you have to lift your manifold to a higher dimension, and the more you the better the approximation you want, the higher dimensional manifold you need. So that's one tiny flaw with this theorem. But it does say somehow that the Euler flows have no additional structure beyond being incompressible. Yeah, since then, some other authors were able to get further universality results. So you can also study stationary Euler flows that don't change in time, but they solve the stationary Euler equations. And those flows turn out to be quite universal. That any, in fact, any vector field which is called geodesical, that there exists a metric on the flow such that the vector field, the vector field trajectories are geodesics. So any geodesical vector field actually can be represented as a stationary Euler flow. You may have to embed your original manifold into a larger manifold, but you can always do it. So this is a nice result. Actually, this is the first time that you had to start using some tools from contact geometry, actually. They worked with a special type of stationary Euler solution called a Beltrami flow, which turns out to be equivalent, essentially, to a notion in contact geometry called a Reeb vector field. And they were able to use the theory of Reeb vector fields to actually do this. So one nice consequence of this actually is that there exists a stationary Euler solution, a solution to the Euler equations, which is a Turing machine, a universal Turing machine. So it creates a certain vector field on a certain manifold. And if you have any Turing machine and you want to know whether it holds or not, you can encode the Turing machine as a certain initial data, a certain point on this flow. And if you start looking at the particle trajectory of this flow, if you ask, does it, and you designate a certain halting region, you ask, does this particle flow hit this halting region? This will be true if and only if the Turing machine holds or not. So in particular, there are choices of initial data for which it is undecidable whether the flow will actually ever hit this halting region. This isn't exactly the universality that I was looking for, but it is some sort of universality. It's a stationary universality. I wanted a time-dependent universality. But it does, again, illustrate that these Euler flows are quite complicated and can exhibit pretty much arbitrary behavior. So I think this was first done in high dimensions, but more recently it was done in 3 dimensions. And there's a variant of this result. In odd dimensions, there's some topological arguments that show that maybe not every vector field comes from a stationary Euler flow, but every vector field can be deformed. It's in the same homotopy class as a stationary Euler flow. So there are some properties of vector fields that are homotopy invariant, such as topological entropy. And so there are you can construct vector fields with positive entropy, and so therefore you can construct Euler flows, stationary Euler flows whose vector field is has positive topological entropy. So there exist very chaotic stationary Euler flows. So this wasn't known before. The only explicit examples of Euler flows that were known before were very rigid. Another recent result, is that let's see. Okay, so so in fact, any vector field on any manifold can actually be embedded as an invariant manifold of a larger manifold, such that if you look at the Euler flow on the larger manifold, it can be arbitrarily close in the smooth topology to the designated vector field. So any finite dimensional dynamics you like can be approximated by some collection of some finite dimensional collection of solutions to Euler equations. But you have to accept a small error. So again, so this means that any dynamics which you can see on a compact, any smooth dynamics on a compact manifold, which is stable under perturbations, for example, having exhibiting homoclinic intersections or something, will also occur for at least one Euler dynamics on some manifold. So this result actually builds upon my previous result where you can embed quadratic flows. And then basically there was a Stone-Weierstrass argument that once you can approximate quadratic flows, you can actually approximate any other smooth flow by a certain approximation of the nonlinearity. Okay. So as one application of this result, very recently, it was shown that the Euler flows can actually be Turing complete. That so not only are the stationary Euler vector fields Turing complete, but actually the actual Euler flow is as complicated as a Turing machine. So there is a manifold on some high dimension, compact manifold, such that if you want to know whether a Turing machine holds or not, you can convert that Turing machine into an initial state, some initial velocity of this Turing of this manifold, and the Turing machine will hold if and only if the flow, the Euler equations applied to this initial data, will reach a certain region of phase space. And so you can convert Turing machines into Euler flows, which tells you, for instance, that that solving these Euler equations is basically undecidable. And this was a surprise. Actually, this actually disproved a conjecture. There was a conjecture actually that analytic maps on a compact manifold could not be Turing complete, but actually this construction shows that they actually can. So we now have a lot of universality results. So we can actually create computers. Okay, so basically what this shows is that high dimensional compact manifolds or fluids can actually act like computers. You can actually program things. So does this mean that we can start programming blow-up solutions that blow up at smaller and smaller times? Unfortunately, there was a problem which I didn't fully appreciate until recently. When I was working in a flat space, in our Euclidean space, there's this scaling symmetry that anything you can do at one scale, you can rescale, and you can do it at smaller scale. So if at a larger scale, you can make a fluid push its energy into a smaller copy of itself, you could rescale and iterate, and you can get blow up in principle. But manifolds, unfortunately, don't have scaling symmetry. When you rescale a manifold, you get a different manifold. So just because your manifold is designed to exhibit universal behavior at one scale, it doesn't necessarily exhibit universal behavior at smaller scales. And so these constructions as of yet do not, they can't be chained together at infinitely many scales to create an actual manifold that blows up in finite time. I'm still trying to make it work. I'm hoping to maybe take a product of Euclidean space and manifold, so you have partial scaling in one direction. It's still not working, but I'm still trying. So this is a long-term project. It's probably quite difficult, but it'll be fantastic if it worked. I will mention one thing. As I mentioned earlier, it was work, so not of Hu and Liu, it's Hu and Chen. There is a breakthrough in this area, but not using this universality, that if you take the axisymmetric Euler equations in 3 dimensions outside of a cylinder, so you have a boundary, using a very different approach, stability analysis of a self-similar blow-up. I mean, the blow-up is still self-similar, but they don't try to use universality. They use more traditional stability methods. They actually were able to prove finite time blow-up, but only with a boundary. But hopefully, well, there's a chance that maybe some of the ideas that they have can be combined with the ideas that I talked about here, and maybe we can actually get blow up for Euler without a boundary. But that's still work for the future. Okay, so that's it. So thank you for your attention.
Thank you very much, Professor Tao, for this very inspiring talk. So we are open for questions. If someone has question, please just raise the hand, and then we will activate the microphone. Maybe, so I saw someone, Elena Velázquez. So
Antania.
okay. So Elena, you can unmute your microphone. And Tanya, okay. Okay, Tanya?
Hi, how are you doing?
I'm very good. Okay.
Thank you so much for your interesting talk. And well, I would like to appreciate that you put the references to generic nature's works, because I was invited once to come to Prague University to commemorate his memory.
Okay.
Professor Nature's. And another question of mine is about the Novikov model.
Yes.
that you demonstrated, because I always think that for example, for dynamical system, if you consider a continuous evolution equation, and then just you apply a finite difference for time derivative, then you land to a difference equation.
Yes.
And then I saw your nice presentation. Then I thought perhaps one can find it would be a second order continuous equation behind the Novikov model that you demonstrated, because there are three sub-indexes, n-1 and n and n+1. But I'm not sure if it's possible. That would be a suggestion.
Right. I apologize. The fire alarm has just gone off in my office. But
yes, this one, because yes, yes, this one, yes.
Okay. Yes. Yeah. So in this model, we have we keep time continuous. So time is still continuous, but frequency we discretize frequency. So that's how these shell models work. We could also discretize time as well, but then we would not. Then you cannot get blow up because blow up requires the time intervals between moving from one scale to the next to shrink to zero. So these are the simplest models where you can still hope to get some sort of blow up.
Yeah, I see your point. It's a discrete continuous one, and it's not possible. I thought then, because for the n, I would thought about another continuous variable there to find out if it would be a continuous derivative behind it. But I would, and then one can, in continuous way, one can solve it numerically, for example, and find out the blow up with a numerical method. That I thought would be.
It's possible you could take a continuous shell model. I've not seen that studied much in the literature, but it's an interesting idea. But yeah, I think that people find the discrete models a little simpler to analyze. That's a nice idea.
But what I would just would like to also as a university professor, I would like to ask you perhaps have a look on this problem, because then we teach dynamical system. It's a splitting between discrete and continuous one, and all these things. Perhaps it's a monography missing that we should really have a look on this problem and connect this continuous and discrete stuff together. And may I ask another question, because I have been studying a lot of your works, and you're an expert for me in Turing machine, in Turing theories. And I have a question about Turing work, about the Turing work of 1936. Then he told that real numbers are computable ones. That's would you help me, because I do not see how with a Turing machine you can always obtain a real number during a finite steps with a Turing machine. Could you explain that? Because for me, you're an expert in Turing.
Okay, maybe you can email me or something. That sounds like a more.
Yes,
okay, thank you so much. Yes, it's bye.
Yeah.
Okay, thank you, Tanya. Thank you, Tanya, for your questions.
Thank you for your talk. Thank you. Yes.
Okay, so maybe inspiring. So Gabriel Barrios wants to ask something. Gabriel, you can activate your microphone now.
Thank you very much. And thank you, Terence Stowe, for the speech. I just wanted to tell, I just started to study both symplectic and contact geometry for a while. So I got interested about, you mentioned that you can approach this problem with contact geometry. I wanted to ask, what should I do if I want to make some research on contact or symplectic geometry and perhaps applied it to open problems in physics?
Well,
or some other fields?
I mean, the easiest way to get into a field is to collaborate or have an advisor in that area. I mean, I myself, I started in harmonic analysis, and the reason I got into PDE actually is that when I came to UCLA, I wanted to mostly do harmonic analysis, but actually the people that I wanted to work with, they actually left the department when the year I arrived. So I instead talked to some postdocs and some other people in PDEs, and I got very interested in PDEs. So it's mostly, I mean, it's very hard to do these things all by yourself. But yeah, if you can find someone in this area and just talk with them, I mean, all these questions, I mean, these problems, it's hard to do things by oneself.
Yes.
Usually you have to collaborate. So, I mean, if you're at a good university, there should be people that you can talk to who can either answer questions on these topics or direct you to other people who can, if you're interested, for example, in the connection with Navier-Stokes and contact geometry, I mean, you can contact some of the authors of the, I'm not an expert on contact geometry. I was amazed when these authors started finding these connections, but you can read their papers and ask them questions, but most people are happy to answer questions by email.
Yeah, it is very interesting to see these relations. Yes. Yes, if you have any contact, I will appreciate it. Thank you.
Thank you, Gabriel. So maybe I have a question about myself about this constraint, this inequality theta less than or equal to 3 over 2 minus alpha over 2. Yes. My question is if do there exists a similar shell analysis for values different of alpha equal to 0 and theta equal to 3 half?
Yes. Yeah. So if you have different values of theta and alpha, yeah, that corresponds to different exponents in over here. I think you can. I didn't write it down here, but I think increasing alpha corresponds to increasing this 4/5 and sort of making the viscosity effect stronger. Yeah, so it's buried in this fraction here. So there are analogs of this shell model for any level of intermittency.
Okay, thank you. And sort of other question, maybe what about to analyze these Euler equations or Navier-Stokes equations in the case of, okay, you have your partial derivative, you have your transport effect, but on the right-hand side, let's say you can put your coefficient and one sublaplacian, one Pomander sublaplacian. If it has some geometric meaning or not, or if it's...
Okay, I've not seen sublaplacians before, but I mean, so one very popular variant of Navier-Stokes is you can replace the Laplacian by a power for Laplacian.
Okay.
So that's called hyperdissipation if its power is bigger than 1, or hypodissipation if it's less than 1. And that again corresponds in the shell model. That corresponds again to changing this exponent. Yeah, it's just modifying the strength of the viscosity. And so people do have results of that type. For example, one thing that's known is that if you take a power of Laplacian that's bigger than 5/4, then you actually have global regularity. In principle, you could work on, for example, a Heisenberg group and take sublaplacians. There's probably literature on that. There are literally thousands of papers on Navier-Stokes. So okay. I'm sure I've considered this problem, but offhand, I don't know of any references.
Okay, thank you. And maybe last question, I promise, that about how much in your construction, in your theorem, when you construct an explicit metric, how much you involve the legal structure of this group that you consider S of 3, I suppose?
Yeah, it was important I had a lead group because it, so it turned out that if I wanted to embed this ODE into the Euler equations, if you do it naively, and just as this, you write down a system of constraints on your metric, there are more constraints on the metric than degrees of freedom. So the problem is overdetermined, and you do not expect a solution. But if you assume some symmetry, I had to assume the metric was invariant, like either left or right invariant. So there was some invariance that I assumed using this group. By imposing the right sort of invariance, I can reduce the number of equations to be less than the number of unknowns. And I could make the problem underdetermined. So yes, the symmetry was actually very important in order for this to work.
Okay, thank you. Maybe we have one question from one of our participants. Maybe it's more about outreach activities. He said, why are the Navier-Stokes equation P=P problems listed as separate problems in the Millennium problems? I think
they're both important problems, and they come from different fields. So the PDEs and mathematical fluids community care about Navier-Stokes, and the computer scientists care about P equals MP. Okay, so all right, in this talk we saw there is maybe a little connection between P equals MP and Navier-Stokes.
Yes.
It doesn't mean though that if we solve Navier-Stokes, it doesn't mean that we solve P equals MP. If we solve P equals MP, it doesn't mean that we solve Navier-Stokes. There's a we can solve both. This is ad for I think Taco Bell or something in the US, and the tagline is "Por qué no dos?" Why not both? There's some girl trying to choose between two different menu items or something, and she ends up saying that she wants both. So I would love Navier-Stokes to be true and P equals NP to be true, or P equals NP to be solved. The belief is that P is not equal to NP.
Okay.
But, yeah.
Okay. Thank you. Yes. Thank you very much. I will stop. Maybe your sharing, Professor Tao. Thank you very much for your time, and we will just let's say thanks to Professor Tao for support our Latin American conference. So thank you very much. Okay, thank you. So maybe for Professor Tao, and also I saw here Professor Carlos Koenig before, we will have in half an hour the ICMAM prize, one prize that in this conference we will award to one Colombian mathematician. Maybe it could be of your interest. So thank you very much, and see you in 30 minutes.
The one? Okay.
Dime.
I would like to remember if everybody have questions, you can do this question in Portuguese, English, or Spanish. This isn't problem. We will try translate for you.
Okay,
si alguien tiene alguna pregunta en español, en inglés, en portugués, pues quería decir que no se cohíban de preguntar, que nosotros traducimos.
Y lo puedes decir en portugués por mí.
Se alguém tem alguma pergunta em espanhol, português ou inglês, pode fazer, tá? A gente traduz para vocês, beleza? Obrigada, thank you, gracias.
Yeah, if you have some questions, remember you can do it and we can make the translation, no? Suena un eco, Duan.
Sí, perdón. Tengo
Ahora,
el computador de servicio técnico al lado.
Ya está bien.
Muy bien, la profesora Tatiana está, ¿verdad? La profesora Tatiana.
Ujú.
La profesora. Los permisos de co-host. Muy bien. Colegas.
Colega.
Hola,
Profesora.
¿cómo le va?
Profesora, acá feliz de tenerla con nosotros. Le presento a Karina González
Mucho
Hola,
gusto, profesora.
y
¿Cómo
a
estás?
Jessica González.
hola, ¿cómo está?
Bien, bien.
Muy bien, profesora. Entonces, pues en 4 minutos nosotros haremos un discurso, presentaremos un video y al
Ujú.
final estaríamos felices si comparte unas palabras.
Gracias. Vi la charla de Terry en YouTube y realmente salió muy bien. O sea, no entré al Zoom, sino que lo hice por YouTube y funciona muy bien.
Qué bien escucharlo.
Sí.
Qué bueno, qué bueno.
Estuvimos haciendo, Brian Grajales,
Varias pruebas.
que está aquí, es el presidente de la conferencia. Él estuvo haciendo todas las pruebas en YouTube. Brian, preséntate tú, mi amigo.
Buenas tardes, profesora. ¿Cómo está? Mucho gusto.
Mucho gusto, ¿cómo le va?
Muy bien, bien. Gracias.
Gracias. Estaba diciendo que vi la presentación de Terry en YouTube y estaba muy bien. O sea, salió perfecta.
Ah, no, qué bueno. Sí, pues ahí el equipo técnico de la Universidad del Valle y aquí en la Universidad de Pamplona nos ayudaron para que saliera bien la transmisión.
Qué
Por
bueno.
suerte todo ha ido bien.
Y Brian ayer a las 5:30 de la mañana, conectándose para tener todo listo. ¿Hace cuánto visitó Colombia, profesor?
Hace 2 semanas.
Qué bueno escuchar.
Sí,
Caramba, genial.
Sí.
¿Qué ciudades estuvo?
¿Dónde estuviste?
Estuve en Bogotá, fui a ver a mi papá y a mi mamá. Mi papá y mi mamá todavía viven y entonces en general fui 5 días y me devolví. ¿Sabes?
Ay, qué rico. Yo también estuve por allá hace ya una semana. O sea,
Ya,
por un mes y me regresé hace una semana.
ya veo. ¿Y dónde está?
Mi familia es de Cali. Y yo en estos momentos me encuentro en Alemania. Perdón.
Ya.
Este es un equipo de jóvenes como usted.
Ya
Bueno,
ve.
yo no tanto, pero
Yo
estas
estuve
chicas son...
mirando y sí, eso me parece muy bien. Eso me parece bien. Sí.
Ni tantos, es solo la cara de jovencitos, ya estamos entrando en edad más.
Yo extremadamente
Engañamos bien.
la juventud nunca se pierde.
Hasta cierto punto, y después el asunto cambia, lamento.
Perdón, creo que Milton,
¿Qué pasó?
nuestro otro organizador, no lo hemos presentado.
Es cierto,
Milton, ya puedes desmutear para que te introduzcas con la profesora. Milton es el encargado en este evento de hacer los videos, mejor dicho, es un todero. Aquí todos somos toderos, el equipo técnico somos todos.
Milton dice que no puede hablar, no sé, no le entiendo qué le dice.
Bueno, muy bien.
Okay.
Entonces, si me disculpan un momento, voy a compartir una fotografía, un collage.
Hola,
ya.
Bruno.
Qué pena, no estaba pudiendo, estaba bloqueado el micrófono para mí. Buenas tardes, profesora. Por ahí alguien más nos saluda.
Sí, Bruno.
Bruno.
Hola, Bruno.
Saludos, Bruno. Qué
Muy
alegría
bien.
ver tanta gente por aquí conectada.
Sí.
Bruno, ¿cómo estás? Es increíble, tenemos amigos por todo Colombia, alrededor del mundo, una participación de más de 40 países. Estamos supremamente contentos con
Sí.
el esfuerzo que este grupo de amigos ha hecho en los últimos 4 meses para tener este.
Bruno no puede hablar, entonces.
El Monte no lo
Ok.
puedo sacar. Ah, ok.
Hola, hola a todos. Es genial esta iniciativa de usted. Yo soy un postdoc ecuatoriano. Me gusta mucho esto. Sí.
Excelente, Bruno.
Genial. Bienvenido,
Gracias
Bruno.
que nos acompañes. Bueno, entonces, ¿qué opinan si iniciamos en punto?
Listo.
Sí, me parece bien.
Ok. Vamos a comenzar. I am going to allow myself to say the following speech in Spanish, but it will have an English translation as before, okay? Buen día, damas y caballeros. Es un placer para nosotros, en representación del equipo organizador del ICMAM 2022 y de su comité científico, dar apertura a la entrega del ICMAM Prize 2022. Esperamos a todos los niveles, desde los más jóvenes hasta los más experimentados, que la comunidad matemática colombiana encuentre inspiración en este hecho histórico y único en su naturaleza. Nos acompañan en esta ceremonia las matemáticas Jessica González Hurtado, quien les habla, Karina Navarro González, organizadora y co-chair respectivamente del ICMAM, y el presidente del comité científico, Duan Cardona.
Good morning, everybody. It's a pleasure for us, on behalf of the ICMAM 2022 organizing team and its scientific committee, to open the ICMAM Prize. We hope that all levels, from the youngest to the most experienced, that the Colombian mathematician community will find inspiration, and the Latin American community also, in this historic and unique event. We are joined at this ceremony by the mathematicians, co-chairs and organizer Karina Navarro and Jessica Gonzalez, and the president of the scientific committee, Duan Cardona.
Permitámonos viajar en el tiempo y tomar partido de nuestra identidad histórica. Hace 40 años, la Academia Sueca de la Lengua otorgó al colombiano Gabriel García Márquez el Premio Nobel de Literatura. García Márquez nos regaló un universo donde todo es posible. Particularmente, le dijo al mundo cuán vasta es la capacidad creativa que puede surgir en América Latina y en Colombia. Hizo parte del gran afamado boom latinoamericano y se consolidó gracias a ello la idea en la que ser un escritor latinoamericano era y sigue siendo una credencial positiva de gran producción y creatividad literaria.
Let us allow ourselves to travel back in the time and take part of our historical identity. 40 years ago, the Swedish Academy of Language awarded the Nobel Prize for Literature to the Colombian writer Gabriel García Márquez. Márquez gave us a universe where everything is possible. He told to the world how much creative capacity can emerge in Latin America. He was particularly in Colombia. He was part of the great Latin American boom. He consolidated the idea that being a Latin American writer was, and still is, a positive credential of great literary work production and creativity.
Hoy, Nos honra anunciar la charla plenaria de la profesora Tatiana Toro. Nos honra anunciar que es la primera galardonada del ICMAM Prize, un premio otorgado por el ICMAM y el Departamento de Matemáticas de la Universidad del Valle, por sus contribuciones en el campo de las matemáticas, más precisamente en el campo de la teoría geométrica de la medida, el análisis armónico y las ecuaciones diferenciales parciales. Nos llena de alegría reconocer su dedicación a toda una vida de trabajo para la visibilidad de la investigación matemática colombiana ante el mundo. Hoy reconocemos la grandeza de su trabajo junto a matemáticos latinoamericanos, íconos de nuestra época como Alberto Calderón, Carlos Kenny, Arthur Ávila, José Fernando Escobar y muchos otros. No es una exageración afirmar que, gracias a científicas como ella, la comunidad matemática colombiana tiene un sello de profunda credibilidad ante el mundo. El mundo hoy es mucho mejor gracias a académicas como la profesora Toro.
Today we are honored to announce the plenary talk by Professor Toro. We are honored to announce she is the first winner of the ICMAM prize, a prize awarded by this event and the Department of Mathematics of the Valle University for her contributions to the field of mathematics, more precisely in the area of geometric measure theory, harmonic analysis, and partial differential equations. We are happy to recognize her dedication to a lifetime of work for the visibility of Colombian mathematical research to the world. Today, we acknowledge the greatness of her work to get together with Latin American mathematicians and icons in our time, such as Alberto Calderón, Carlos Kenny, Arthur Ávila, José Fernando Escobar, and many others. It is no exaggeration to say that thanks to scientists like the Colombian mathematical community has, the Colombian mathematical community has a stamp of deep credibility in the eyes of the world. Thanks to academics like Professor Toro, the world is much better today.
La profesora Toro ha publicado su trabajo en revistas de gran reconocimiento internacional: The Journal of Differential Geometry, Duke Mathematical Journal, Annals of Mathematics, Advance in Mathematics, Geometric and Functional Analysis, Journal of the American Mathematical Society, The Journal of Geometric Analysis, Mathematische Zeitschrift, entre otros.
Tatiana Toro has published her work in international renowned journals, like Duan Cardona said before.
A continuación y hasta este momento hemos reservado algunos detalles biográficos de nuestra primer ICMAM Prize 2022.
We have reserved some biographical details for our first ICMAM prize. So go ahead.
La profesora Tatiana Toro nació en Bogotá, Colombia, en 1964. Su primer acercamiento a las matemáticas lo tuvo en la escuela primaria cuando participó de una inmersión en una escuela francesa, donde tuvo la oportunidad de interactuar con conceptos matemáticos de una manera lúdica y divertida. También participó de la Olimpiada Internacional de Matemática de 1981, con sede en la ciudad de Washington, D.C., Estados Unidos. A su regreso, obtuvo el título de matemática en 1986 por la Universidad Nacional de Colombia. Seguidamente, alcanzó el título de doctorado en 1992 por la Universidad de Stanford bajo la dirección de Leon Simon.
Tatiana Toro was born in Bogotá, Colombia in 1964. Her first approach to mathematics was in elementary school when she participated in an immersion in the French school. She had the opportunity to interact with mathematical concepts in a playful and fun way. In 1981, she participated in the International Math Olympics held in Washington, D.C., USA. On her return, she got her bachelor in mathematics in 1986 from the National University of Columbia. In 1992, she obtained her doctorate from Stanford University under the direction of Leon Simon.
En el campo laboral, la profesora Toro ha ocupado puestos breves en instituciones como Institute for Advanced Study, Universidad de California en Berkeley y Universidad de Chicago. También fue profesora asociada visitante en la Universidad de Harvard y actualmente es profesora de la Universidad de Washington, a la cual se vinculó desde 1996. Desde allí centra su investigación en la teoría geométrica de la medida, análisis armónico y ecuaciones diferenciales parciales.
In her professional career, Toro has held brief positions in institutions as the Institute for Advanced Study, California University at Berkeley, and Chicago University. She was also a visiting associate professor at Harvard University, and she is currently a professor at the Washington University since 1996, where she focuses her research on geometry measurement theory, harmonic analysis, and partial differential equations.
A lo largo de su carrera como matemática, la profesora Toro ha ocupado diferentes cargos y recibido distintos reconocimientos por su labor como profesional en matemáticas, entre los que se encuentra su participación como invitada en el Congreso Internacional de Matemáticas del año 2010. También se destaca el recibimiento de la beca de la Fundación Simons en los años 2012 y 2019 y la beca de la Fundación Guggenheim en el año 2015. Fue elegida Fellow de la American Mathematical Society en el 2017 por sus contribuciones a la teoría geométrica de la medida, a la teoría del potencial y a la teoría de frontera libre. La profesora Toro fue galardonada en el año 2020 con el premio Blackwell Tapia y elegida miembro de la Academia Estadounidense de Artes y Ciencias en ese mismo año. En el año 2021 se anunció su elección como directora del Mathematical Sciences Research Institute para el periodo 2022-2027. Y este año, en la conmemoración de la 19ª Asamblea General de la IMO, International Mathematical Union, fue elegida como vicepresidenta para el periodo 2023-2026.
Along her career as mathematician, Toro has had different positions and awards for her remarkable work, including her participation as a guest at the International Congress of Mathematics in 2010. She also received the Simons Foundation Fellowship in 2012 and 2019, and the Guggenheim Foundation Fellowship in 2015. She was elected member of the American Mathematical Society in 2017 for her contribution to geometry measure theory, potential theory, and free boundary theory. Toro was awarded the Blackwell Tapia Prize in 2020. An elected member to the American Academy of Arts and Science in the same year. In 2021, it was announced that she will be elected director of the Mathematical Science Research Institute, MRSI, from 2022 to 2027. And this year, at the commemoration of the 19th General Assembly of the IMU, International Mathematical Union, she was elected as Vice President of the period 2023-2026.
Ahí.
Muchas gracias. Me honran y me hacen sentir vieja, pero bueno, realmente pues, quiero agradecer mucho el premio, quiero agradecer mucho el honor y quiero sobre todo indicar que yo soy uno de los muchos colombianos que estamos haciendo matemáticas, que he tenido la suerte de haber sido reconocida, pero que realmente somos muchos y que no a todos tienen la oportunidad de ser reconocidos de la misma manera. Una de las personas que fue mencionada inicialmente fue José Fernando Escobar, Chepe Escobar. Yo quisiera tomar un minuto para recordar a Chepe, quien fue muy importante para Colombia, para las matemáticas en la Universidad del Valle y para el análisis geométrico mundial. Y también quisiera agradecerle a Chepe el hecho de que él siempre me apoyó. Yo realmente, en particular al principio de mi carrera, cuando lo conocí en los Estados Unidos, yo sabía que podía contar con él y fue una pérdida muy grande para las matemáticas el haberlo perdido tan joven. Pero ya que lo quisiera recordarlo y agradecerle todo lo que hizo. Realmente me siento honrada y me hacen sonrojar. Yo no soy buena para hablar, dar discursos, pero quiero simplemente decir muchísimas gracias.
Muy bien, profesora.
Gracias
Es
a usted, profesora.
con todo el amor del mundo, como dicen los colombianos. Entonces, no sé, en este momento los invitamos a desactivar su micrófono y a dar un aplauso. ¿Alguien lo dice en inglés?
Turn off our microphones and give an applause to Tatiana of work. We are so proud of her and all her work are how she's giving to the Colombian mathematical work all the honors and like giving all our culture abroad of our country, and we are so proud of her.
Profesora, muchas gracias por sus palabras, gracias por apoyar nuestro evento. Usted apoyó nuestra iniciativa desde el inicio. A veces no es fácil organizar eventos de esta naturaleza y invitar, tener, digamos, investigadores consolidados como usted y como los colegas suyos que hemos invitado a esta conferencia. Le agradecemos. Y pues bueno, solo nos queda esperar su charla plenaria en cerca de 10 minutos.
Bueno, me dice cuándo quiere empezar. Yo quisiera decir, una de las cosas que no hay que, lo voy a hacer sonrojar, pero una de las cosas que han hecho mi trabajo mucho más agradable y que lo han hecho estimulante son las personas jóvenes, o sea, los estudiantes y los postdocs con quienes he trabajado, y Bruno es un ejemplo de esa generación. Cuando en el 2017, en este momento estoy en la oficina de MSRI, que ahora se llama ICMAM, y la última vez que había estado aquí en un programa, Bruno estaba aquí como estudiante y había un grupo de estudiantes que estaban y de postdocs que estaban trabajando juntos y que hicieron un número de cosas muy interesantes desde el punto de vista matemático. Eso siempre nos ayuda. O sea, uno siempre opina que son las personas que son mayores los que nos ayudan. No, son los jóvenes también los que nos estimulan a seguir. Quiero agradecer a esa generación por todo el estímulo y porque son la razón de seguir adelante.
Muchas gracias, profesora. Muchas gracias a Bruno por estar presente. Sí, en el marco de la conferencia también, estamos honrando a uno de nuestros maestros de la Universidad del Valle, el profesor José Raúl Quintero, del Premio Nacional de Matemáticas. Entonces le invitamos a la profesora Toro también pues el honor, el tributo que se le hará al profesor el viernes, en caso de que tenga tiempo libre.
Gracias.
Profesora, muchas gracias. No sé si los organizadores quieren comunicarle algunas palabras a la profesora.
Yo solamente quería darle las gracias también. Ella dice que nosotros desempeñamos un papel importante, pero claramente con el ejemplo que tenemos, ¿cierto? En sus manos y en las manos de todos estos grandes matemáticos consolidados, pues nos motivan cada día a continuar esta carrera que no es fácil, ¿cierto? Y pues creo que es eso lo que yo quiero decir.
Bueno, por mi parte, como mujer en matemáticas también es muy bonito tener una referencia, ya que esto está lleno de hombres y también a veces uno siente mucho la competencia que hay en varonil, ¿no? Entonces también sentir tener esos ejemplos femeninos y saber de que en realidad todo el mundo tiene la oportunidad, esto no depende de nada y que hay que trabajar fuerte, todo el mundo trabaja fuerte, es muy, como que uno se llena de más ánimo para seguir luchando y darle todavía aún más, ¿sí? Entonces, es muy agradable tener mujeres en matemáticas y pues mejor si es una paisana colombiana que le hace... Sí se puede, sí se puede. Entonces,
Claro que sí, Omen, claro que sí.
Muy bien.
Sí, es una cosa que siempre les digo a mis estudiantes. O sea, cuando yo decidí que iba a estudiar matemáticas acá en Colombia, o sea, yo soy mayor que todos ustedes, tal vez todos ustedes juntos, y no, en ese momento realmente no era claro lo que uno hacía con un título de matemáticas, y la verdad es que cuando yo vine a hacer el doctorado en Stanford, yo seguía sin saber qué hacía uno con un doctorado en matemáticas. Yo sabía, o sea, yo quería hacer más matemáticas, y entonces el punto es que yo creo que uno debe soñar grande y seguir el sueño. Y claro, alguien me decía, sí, eso es muy fácil de decir, pero ¿qué hace con los obstáculos? Pues los encuentra, se cae, se vuelve y se para, se sacude y sigue, porque, o sea, no siempre es así de fácil, pero si uno sueña grande, realmente llega lejos, ¿no? Tal vez hasta donde sueñe, pero sí llega lejos. Uno tiene que permitirse soñar grande.
Gracias.
Sí.
Y con respecto a lo que dice Jessica, una de las cosas que de vez en cuando digo, o sea, yo tengo familia, mascotas, o sea, tengo todo lo demás que viene, no solo el trabajo, porque a veces uno piensa solo un lado y no el otro, no, realmente sí, viene el paquete completo.
Muy bien.
Sí.
No, pues profesora, agradecerle por sus palabras. Justamente la profesora Alicia Dickenstein nos insistió bastante. Muchachos, yo quiero que haya participación de mujeres matemáticas en el evento y intentamos siempre
Sí.
tener este equilibrio. Bueno, profesora.
¿Le
Entonces,
parece si ensayo a compartir la pantalla para que nos aseguremos que está bien?
sí, profesora. A continuación.
Porque es que voy a hacer una cosa que no he hecho antes, entonces por eso es más, digamos, el chequeo técnico de este lado que del otro lado.
Muy bien. Adelante.
Cruzamos los dedos. ¿Qué están viendo?
Su transparencia que dice Geometry of Measures.
Ah, bueno. Qué maravilla. Porque yo estoy viendo que están viendo otra cosa. Entonces,
Ok.
pero yo creo que espérense un poco. Y ahí la vieron pasar, ¿correcto?
Vimos pasarla, sí.
Perfecto. Listo. De sí funciona. Está un poquito. Sí.
Ok. Ah, muy bien. Usted está viendo la transmisión desde YouTube, ¿verdad? ¿Nos dijo
No,
antes?
yo vi la charla de Terry desde YouTube,
Ah, ok.
pero no, ahora estoy en Zoom común y corriente, porque si no,
Es cierto.
puede que lo otro se pueda, pero no voy a ensayar.
Ok. Ok. Pensé que había compartido la otra.
No, estoy compartiendo desde, ¿cómo se llama? Desde Zoom, pero lo que pasa es que tengo dos monitores y lo tenía ya en slideshow, entonces no sabía si iba a funcionar o no.
Muy bien. ¿Y planea escribir sobre las transparencias? O...
No.
No,
No, o sea, esa era la otra opción, pero decidí que no. Van a tener que en algún momento que mirar las manos, pero no.
Está bien.
No creo que pueda. No sé. No.
Sí.
O sea, si lo hubiera hecho desde mi tableta se podría, pero entonces las transparencias no se ven igual de bien. Entonces,
Sí. Profesora, una pregunta. El MSRI cambió de nombre a la actual. ¿Hay una razón? No conozco la razón de
sí.
fondo.
Entonces, dice ICMAM, que quiere decir Simons Laufer Mathematical Sciences Institute. Fue un regalo de dos familias, Simons, Jim Simons, Jem and Mary Simons y Henry and Marshall Laufer. Es un regalo muy grande de fondos sin ningún tipo de restricción que nos permite seguir.
Se mutó. Creo
Se
que está mutada, profe Tatiana.
Sí.
Profe, disculpe, yo muteé porque
Sí,
había un
sí.
ruido externo y disculpe, por favor,
Listo,
continúe.
no se preocupe. Entonces nos dieron, es un regalo de fondos que no tienen ningún tipo de restricción, que nos permitirán seguir haciendo lo que hemos estado haciendo e incrementar el número de programas. Nosotros tenemos, entonces, el acuerdo era que si había un regalo de esa magnitud se cambiaría el nombre, o sea, eso fue una cosa decidida antes de que yo llegara y eso fue lo que pasó. El presupuesto científico, las 2/3 partes están financiadas por la National Science Foundation, pero el resto no. Y nosotros tenemos, además del presupuesto puramente científico, tenemos un número de programas adicionales que cada año tenemos que buscar financiación. Y entonces esto nos ayuda a hacerlo. Programas como, por ejemplo, escuelas de verano. El año pasado tuvimos 12 escuelas de verano. El año entrante esperamos tener de 12 a 14. Algunas son aquí en esta área, pero muchas de ellas son colaboraciones internacionales. Y entonces, para poder financiar eso, una de las cosas que quiero hacer, en parte en conexión con haberme vuelto vicepresidenta de la AMU, la otra persona que es vicepresidente de la AMU es Ulrika Tildeman, que éramos ambas estudiantes en Stanford más o menos en la misma época. Ella es la directora del Newton Institute. Hicimos una escuela de verano juntas, los dos institutos el año pasado, y hemos hablado de tal vez hacer escuelas de verano juntas que también tengan colaboraciones con otras áreas del mundo, por ejemplo, la que está basada en Inglaterra. Hemos hablado con algunos de los institutos en África a ver si eso se podría hacer desde aquí. Nosotros tenemos colaboraciones con la Casa Matemática de Oaxaca, con BEERS, pero también mirar otros institutos para tratar de, digamos, de beneficiar un poco más globalmente a los estudiantes de posgrado. Entonces, pero esas cosas son cosas que no están financiadas, digamos, que serían expansiones que necesitarían fondos nuevos, y por eso es que es importante esta donación que tuvimos.
Muy interesante, profesora. Bueno, en todo caso, el director del Ghent Analysis and PV Center es el profesor Michael Ruchansky y tiene iniciativas bastante similares. Él, por ejemplo, acoge estudiantes de doctorado de países en vía de desarrollo, Kazajstán, entonces va a Uzbekistán y esto. Entonces, bueno, quizá en el futuro podría comunicarse con él para extender desde este lado.
Sí.
Seguramente estaría muy interesado.
Sí, hemos comenzado, antes no teníamos estudiantes de posgrado, ahora hemos comenzado, no había financiación, ahora tenemos financiación para algunos. Hay condiciones de quiénes son elegibles, pero sí tenemos algunos y pues realmente los estudiantes de posgrado son el futuro, y esto es una inversión en el futuro. Entonces, por eso es importante mirar qué se puede hacer en esa área.
Interesante, profesora. Bueno, estamos solo a un minuto de comenzar. Usted fue, creo, compañera del profesor Andrés Villaveses, ¿verdad? De la Universidad Nacional.
No,
No
realmente
realmente.
Andrés se va a ofender. Andrés es 5 años menor que yo. Él fue compañero. No sé si, o sea, como está detrás, no, se puede que se sonroje, no. Andrés era compañero del colegio de mi hermano, que es 5 años, 4 años y medio menor que yo. Yo era compañera de Guillermo Rodríguez, que también sí. Pero...
Entiendo. Porque con el profesor justamente 2 años atrás iniciamos un proyecto y es en pro de ese proyecto que estamos gestionando conferencias y queremos expandir de pronto un poco este tipo de iniciativas porque hay un sueño colombiano detrás que estamos, digamos, vemos a futuro con el profesor Villaveses y es la creación de un Instituto Colombiano de Matemáticas. Entonces es una apuesta pues, a largo plazo y tenemos eso en mente, En el futuro, quizá va a tomar muchos años con toda la burocracia colombiana, pero lo tenemos en mente, profesora.
En algún sitio hay que empezar, ¿sí?
Sí. Incluso uno de nuestros maestros, Gonzalo García, desde la Universidad del Valle, él nos dijo, muchachos, deberían crearlo así fuese de forma virtual. Deberían crearse un instituto de matemáticas, inician de forma virtual y luego se extienden, piden financiación. Entonces tenemos ese sueño y allí vamos. Profesora, no le quito más tiempo.
Gracias.
Karina.
Sí.
¿Quieres presentar a la profesora?
Quiero. Bueno, sin más preámbulo, entonces vamos a dar inicio a la conferencia de la profesora Tatiana Toro. Puedes comenzar, profe.
Estás mutada de nuevo, profesora.
Ok, ahora sí.
Perfecto.
Sí. Y vamos a ver si funciona, porque ya vi que había algo que no estaba funcionando. En ese caso tengo que entrar y volver a salir. Ok, pero todo me voy a disculpar, pero yo en general voy a hablar en inglés. Me pueden hacer las preguntas en castellano y yo trato de responder en castellano, pero no garantizo. Okay, so what am I going to talk about? I want to talk about whether the infinitesimal properties of a measure, and I will describe what these mean, in Euclidean space determine the structure of the support of the measure. So the 3 questions I want to address is, what type of properties am I talking about? What type of information about a measure could I get? And does this depend on how I measure distance in Euclidean space? Okay. And so as Terry said a little bit, I'm going to describe, so I am also going to talk a little bit about things I would like to be able to do, or we would like to be able to do, but we're not there. So I'm going to give you the history of the problem. I'm going to tell you what we really wanted to do, and then I'm telling you what we really are able to do, and then leave some open questions, okay? And now, I'm sorry, I'm gonna need to get out. So I'll be back. Sorry. My computer is jammed.
No problem.
Okay, we're gonna do something else. Give me a minute. So it was working great, but now it doesn't work.
Okay.
Okay, no, now let's go back. It's a little bit peaky today. Share. And let's see if I can put it in full screen. Okay, let's see if it works now. Okay, so metrics in Euclidean space. So let me remind you how we measure things and what's a metric. This is very basic, but I just wanted everybody to be on the same page. A metric of the distance on Rm is a function such that is symmetric. So the distance between x and y is 0 if and only if x equals y. The distance between x and y, is the same as the distance between y and x. And there's a triangle inequality. So I am assuming we all know these, and I'm going to give you 2 examples. This one is the distance, so you take the sum of the difference of the components, and rather than taking one, which is what we often do and will do here when P is 2, I put a number square. So I will give you some, there will be pictures in the next slide. So this is a distance. And then for P greater or equal than 1, this dP of xy is the sum of yi minus xi to the P, 1 over P. And this is just the little LP norm between x and y. And one of the things I'll remind you is that all metrics in our M are equivalent, okay? So what does that mean? That if I measure the distance between 2 points this way or this way, one is bounded above and below by the other, okay? So in RM, theoretically, when you look from the metric point of view, there's only one distance. Oh la la. Okay, so what are the balls? For the first metric, these are what the balls are. So what do I mean? If I say, let's take, this is the point X here in the center. If I say the distance between X and Y is less than 1, then some of, depending on what the AIs are, these might be some of the balls, okay? So the ellipses are balls. And then for the little LP, if P is 1, this is the unit ball. I assume that here this is 1. If P is 2, this is the unit ball. So when I say ball, we all think of the round ball. But for example, when P is 8, this is what my unit ball looks like. So that means if I put, dP less or equal between 0 and x less or equal than 1, this is the picture I get. And when I put P equals infinity, this is the unit ball. And the fact that the two metrics are equivalent means that, for example, inside these balls, any of the balls all contain a round ball, and they all contain a round ball. So distances are more or less the same. Okay. Please don't hesitate to ask me questions. And again, it's not, I am very sorry about this. For some reason, it's not working. My apologies. Okay. There's a huge delay. Okay. So let me remind you a couple of properties of Lebesgue measure. So Lebesgue measure is the measure that we use on the plane. And so just if you take any of these metrics, any of them, and you take a point X and a radius R, you know that the Lebesgue measure in Rn is exactly omega n r to the n. It's, so what do I mean? It's a fixed number, the measure of the unit ball, times a power of R, and is independent of the point X. And the following other relationship is also true. This is not as important for this talk, but it's also something that we have. So that's, this is something we can all compute. You're going to say, why is she doing that? Well, you'll see in a minute. Then if I have a measure, a locally finite measure in Rm, I call the support the set of points X in Rm such that the measure of the ball of centered X and radius R, and here I don't care how I'm choosing ball, they're all the same, is positive for every R. So this tells me this is something that I am really seeing. This is points that are seen by my measure. Okay. And now here is the question I want to ask. I have two questions. The question is, what can you say about mu if either of these two properties holds? For every X in the support and every S positive for the second one. So the limit as R goes to 0 of mu of B of X R over R to the N, this number exists. And, or if you know that this number is constant, can I say something about the measure? So why am I asking that? Because that happens for Lebesgue measure in Rn. But now imagine for a second that you are, I'm going to give you numbers. Imagine that you have in R, you live in R5, and that you have a measure for which, I don't understand how, sorry.
Don't worry.
So
please
I have
your time.
Okay. I have a measure for which, let's imagine, so I live in R5, M is 5, and I have a measure such that this thing holds with R3. Okay. Mu of B for, and let's imagine for a minute is a round ball. Mu of B of XS is omega 3 S to the 3, and omega 3 is the measure of the unit ball. Do you know who that measure is? Okay, keep that thought. And I'll tell you why that's important and where this comes from. Okay, so that's my question. And so the outline of the talk, I'm going to do a little bit of an introduction to geometric measure theory. I'm going to talk about the infinitesimal properties of a measure and structure of the support for the Euclidean space with the standard metric, D2. And then I'm going to tell you what I really would love to be able to have good results is what happens when we consider Euclidean space with a different metric. Okay. We are told that they're more or less the same. They should be the same, but we don't know. Okay, so from now on, for a little bit until I tell you otherwise, this is what our balls are going to look like. All our balls are going to be round. I'm only talking about L2. Okay, that's where the literature exists. Okay, so remind you from the real analysis class, from the Lebesgue differentiation theorem, the following thing is true. And so one of the things I do when I teach or talk about these, remember Lebesgue, that was the beginning of the 20th century. He, as a long time ago, is the beginning of measure theory. And one of the things that we know is that if you have a subset of E, which is measurable, that has positive measure, then at almost every point, if you look at the interval of radius R around X, you intersect it with E and you divide by the length of the interval, this is going to give you 1. Okay, this is what's called Lebesgue differentiation theorem, a classical theorem and analysis. Now, the Hausdorff dimension generalizes the notion of length to a curve or other subsets of Rn. So, Lebesgue measured is on the line, but imagine you have a curve. Sorry, and now you need to look at my you have a curve, you want to measure the length. That's what the Hausdorff measure does. Okay. So the question that Besikovich asked in between 1928 and 1938, and that was the beginning to this type of ideas, was the following. Imagine you have a set in R2, okay, such that the length, this H1, is positive and finite. So imagine like a curve. And assume that when you measure that length, that the equivalent of these holds. So now you take a ball, round ball, remember round ball, of center X and radius R, you intersect it with E, you divide by 2R, and you know that that limit as R goes to 0 is 1 almost everywhere. What can you say about E? Okay, can E be very bad? And the answer is no. E is 1 rectifiable. I'll tell you in the next slide what that means. But that's basically tells you, philosophically speaking, it tells you that if these, so these, I cannot understand how this works. This tells you that if you are on the line, you have a 1. And here, this roughly tells you that if you behave like what happens in the line, to be rectifiable, it means that infinitesimally, when you look, you stretch and you stretch, you see something like a line. That's what the content of what comes next is. So what is rectifiability? So the n-dimensional Hausdorff measure, Hn, realizes the notion of surface when n is 2, of volume for subsets of Rm. And if you are in the plane, it's exactly the same as Lebesgue measure. And so a set E in Rm is n-rectifiable if it can be included in a countable union of Lipschitz images. So these FJs of Rn, I'll tell you exactly what Lipschitz means, union a set of measures 0. And a function is Lipschitz if there exists an L such that Fj of x minus Fj of y is bounded by Lj of x minus y. So it doesn't distort distance too much. That's a Lipschitz function, okay? So rectifiability means this. You might ask, that doesn't seem very smooth. I thought you were going to tell me that this was a smooth set or something like that. This is a good enough notion of smoothness in this setting. You'll see maybe why I could have written these by the FJs are C1 and I would have had the same result. So it's kind of, but derivatives exist, which is the maximum amount that you can expect here. Okay. So what Besikovich proved is that if the density exists, then your set is rectifiable. And then Federer, and really the field is called geometric measure theory because Federer published a book that's called Geometric Measure Theory. It's a field of mathematics that carries the name of a book. But what he proved is that if n is less than m, E is a subset of Rm, is n rectifiable, then this density exists. So Besikovich, density exists, one density exists, your set is rectifiable. Federer asks, if you're rectifiable, does the density exist? So this number here, which I haven't defined yet, is important clearly. It's called the density. Questions? Okay, so let me define. If I have a locally finite measure in Rm, the n density of mu at x exists if this ratio, the limit as r goes to 0, of mu of b of x r over omega n r to the n, this limit exists and is between 0 and infinity, and is not 0. Okay, and remember, I could make these definition for balls that are not round, but everything I'm talking about here are for round balls. Okay, you'll see what happens as soon as I change the round balls to other balls. Okay. And we say that a locally finite, the other thing was a set, but now a locally finite measure is rectifiable if it's if it's absolutely continuous with respect to Hn, which means if I have a set of Hn measure 0, it has mu measure 0, and mu of Rm minus the countable union of Lipschitz images of Rn has measure 0. Okay, so it's very similar to before, is now for the measure, but it's roughly the same. Okay, so let me tell you what's known. So this is going to be a long table with the whole history. So I'm going to put years and years of work in a table. Let's assume that this number exists, that is between 0 and infinity. And I look at two types of measures. One of them is the Hausdorff measure restricted to a set. So it's like, imagine I have a surface and I'm just looking at the surface measured on that set. The other one is a locally finite measure. I don't know what it looks like. Okay. So in 1938, Besikovich proved that if n is 1 and n is 2, so that's the result I had quoted, then E is 1 rectifiable. So I have a set, a one-dimensional set in R2. If the density exists, it is rectifiable. In 1944, Morse and Randolph proved the same thing, but for the general measure. So you're going to say it's going to be slowly, it's going to go slowly for a little bit. In 1950, Moore went from m equals to 2 to m greater or equal than 2, but you still had a 1. Okay. And the reason why 1 is important is because if you have 2 points that determines a line, and a line has dimension 1. Somehow that's a key part of the ingredient. Okay, in 1961, Marshall was able to do something interesting. He used n equals to 2, m equals to 3, and then e is 2 rectifiable. So he changed the dimension. Okay, and that was an important contribution, and he did many interesting things around that time. Then in 1975, Matila was able to prove the general result for this type of measure, HN restricted to a set. And it took still 12 years until Price in 1987 proved that the general result. So if the density exists almost everywhere, the measure is n rectifiable. This was a very, very, very interesting piece of work. He introduced a lot of tools that had never been used in this area. When you ask him why, he said, because I had friends who were doing statistical mechanics. And so he brought the tools from statistical mechanics to try to understand this problem. And he did an incredible piece of work. So I am in the next slide in 3 bullets. Describe Price's work. It's a very, very rough sketch. So the first thing he did, maybe this is a limit. Remember, limit as r goes to 0. Now, for a second, imagine you're teaching a calculus class. The students have a graphing calculator. You ask them to draw the graph of a function. And you ask the student to decide if this function, if this graph has a tangent at a point. What do the students do? They start enlarging, enlarging, and enlarging the picture. And if they see a line, they're going to tell you it has a tangent. And if they don't see a line, they're going to tell you that calculator is broken because they think that every function has a tangent. But basically, it's enlarging and enlarging. So we do the same thing for a measure. This is a limit. This is an infinitesimal property. I'm going to enlarge and enlarge my support. And that's what Price did. And he looked at what we call tangent measures. And so a tangent measure is to a measure like the derivative is to a function. And it carries infinitesimal information about the infinitesimal behavior of the measure. So first thing Price did, he introduced the notion of tangent measure, and he computed the tangent measures for measures that had density. Then this blow-up procedure, this enlarging, this blow-up procedure shows that the n density, and don't worry, I'll give you the definition in a second, of mu exists at almost every point, and that all tangent measures are n uniform. What does that mean? It means this. So that a measured nu is n uniform if there exists a constant. The same constant works for every point and every radius, such that for every radius and every point in the support, nu of b of xr is cr to the n. Remember, I asked you at the very beginning, try to imagine who those measures could be. So Price did all of these. This is a monumental piece of work. And then the next step is, okay, well, these tangents look good. I gave you an example in a plane. If I am the n-dimensional plane, this works, but are there other examples? And so I am not going to say that it's like a student, that if you get a plane, if I were able to say that this measure nu is flat and it's just like Lebesgue measure in a plane, I would be happy, but it would be a lot of information. So the first question is, who can these measures be? So here is what he was able to do. And I have to say, here it looks like in one slide, but these are like his paper of 1987 is a paper in the Annals that has over 100 pages. So there's a lot of mathematics there. I'm putting them in 1 or 2 slides. But basically, if you're n uniform, which is these, then you are just a product, you're just a multiple of Hn restricted to the support of your measure. Okay, so Price showed that if n is 1 or n is 2, you have to be either a line or a plane. Then Kernheim and Price proved that the support of these measures, so this lambda, is always a real analytic variety. By that I mean is the zero set of a real analytic function, and they use that structure to say many things. And then the incredible, most of the work in the paper then goes into here. It's showing that an n-uniform measure is either flat, which means is good, and if it's flat, it's going to be the plane, an n-plane, or is very far from flat. And you're asking what? Okay, well, but are there examples? Because it looks really weird. So I'm going to give you examples first. They're not. Here is an example. So this was the first example that Price and Kowalski found in 1987 also. If m is n plus 1, n is greater or equal than 3, and you are an n-uniform measure, then you're either a plane or you are a rotation and a translation of the following cone. And so notice that the cone I only cared, you have a cone in R4, x4 squared equals x1 squared plus x2 squared plus x3 squared. So this is the light cone. And so this is an example. The measure of any ball centered in the cone, yes, at the vertex, but more importantly, like, I don't know if you see my cursor, but here, and you take a ball like this size, is exactly omega 3 r to the 3. So this was an example that's not flat. For many years, and this is codimension 1, for many years, there were questions about whether other examples existed. I have to confess, so this was a problem I often mentioned in my class when I taught these. Do other n-uniform measures exist in higher codimension? In codimension 1, these are all the examples, but are they in higher codimension? And my students often like these, and one of my students was very stubborn, and he decided that he was going to look into it. So my student, Dali Neimer, was able to produce, I don't want you to focus on these, but he was able to produce a number of three-dimensional uniform measures in R5. Basically, if they're canonical, he proves that these are all the examples. So there are lots of them. And this is a combinatorial result, actually. And then if you're not he was able to construct a lot of other examples. He cannot say these are all, but he has lots of examples. So these things exist. Okay. So remember, Price was trying to show that it was rectifiable. He wanted to show that the tangent measure was flat, but clearly there are examples of things that are uniform that are not flat. So he had to work very hard to show that at almost every point, all tangents are flat, and then he went from there. Questions? Okay, so clearly, what do you need to understand to do a work like this? You need to understand who the tangents are. Hopefully they'll be uniform in some sense, and then you need to understand the uniform measures. Okay. So the motivating question for lots of the work that I want to describe, that I've been trying to do, and that I have to confess we've had a hard time doing, is the following. We always thought that, so as I said, all metrics in Rn are equivalent. We're always told that roughly measuring in the L2 and LP is more or less the same. So the question, is it true? So from this point of view, so imagine the question is, how does the infinitesimal behavior of a measure mu on LP balls, so the ones that have the little p, determine the geometry of the structure of mu? And more precisely, imagine that for this measure mu and everybody in the support, I can say that the limit at r goes to 0 of mu of bp of x r over omega n r to the n, and this is the measure of the unit ball, LP unit ball in Rn, is between 0 and infinity. So this was the question that we asked with David Bate, Bobby Wilson, and I'll tell you where Max Gehring comes. But so this was the motivating question. And the one reason I want to highlight it is because We have had 2.5 very hard years with the pandemic, and we often focus on all the negative things, but I want to focus on 2 positive things. One, we can have conferences like these. I could not be given a conference talk in Colombia today if I were not able to do it this way. And this work on these was started in March of 2020 when Bobby Wilson was visiting Dave Bate in Warwick. He had to leave in a hurry. And then I thought, well, why don't we continue talking in Zoom, since that's the only thing we can do. We're all at home. And so we did lots of the thinking about this problem and lots of the learning in Zoom from, during the pandemic. Okay, so.
Teacher.
Yep.
Sorry. What is ASPT? I don't remember.
Oh, the support.
Okay, support.
Yeah, support.
Okay. Okay, thank you.
So let me go back. So the question is, what can we say? So what was known is something that's called a Marstrand type theorem. So let me tell you what that says. It tells us when you see n here, you tend to think of an integer. But what Marstrand's theorem tells you is that it has to, for the round balls, that it had to be an integer. So what Andrew Laurent proved is that if this number exists, for here n and s are the same, and s is a number between 0 and 2, and the balls I'm considering are either the squared or the diamond, then s can only be the number 1 or the number 2. Okay, but it's super specific. It is only for these 2 balls. Is only if s is between 1 and 2, and so that's, and you'll see there's very few results. Then,
sorry, can I make a question?
Yes, of course.
Okay, for the limit, let's say this limit depends on p, but let's say if one take limit when p tends to 2, is this there is some continuity for this limit in terms of p, or it's not possible to have something?
Absolutely. So if p were to be very, very close to 2,
yes,
then we will be able to say things, because Price's result is a little bit flexible. He doesn't need the density to exist. He needs the density to be the upper and the lim sup of this number and the lim inf of this number to exist, and the ratio of the 2 to not be very far from 1. And if p is close on 2 and this density exists, then you prove something for the 2 density, and then you can apply Price's theorem. So very close to 2 we can do.
Thank you.
But I cannot tell you how close depends on n and on m. So the environment where you live and the n that you have here.
Okay, thank you.
Okay. And since I want to point out that at least for Laurent, for Marstrand, these 2, when you think of p, these 2 are in some sense the worst possible p's, because these 2 for these 2 p's, you do not have strictly convex norms, and we have a sense that matters. But so in some sense, these are the worst possible case, but it has not been done in the good cases either. I mean, so just to show that very little is known. And this is for the general measure. So you might ask, well, but in the table that you showed us, it looks like if the measure was HN restricted to the support to a set, maybe is easier. And so that's what my colleague Bobby Wilson is doing. And he has, everything seems to indicate that when P is between 2 and infinity, and mu is restricted to the support to a set, if the density exists, then you can prove that your set is rectifiable. So I did not write everything. Basically, what I am, every time I say this is the results, what was known for the round balls is true for these LP balls. Okay, but it's a very specific measure. And it's because when you have such a measure, somehow, if you're seeing the set, it means that you know how much you see the set on both sides. But okay. So what we really wanted, so what did we want? Because I said you have to dream big. And so what we wanted to prove is that if this limit existed, the measure was rectifiable. We are able to do the same thing that Price does, that shows all the tangents are uniform. So we started asking ourselves, well, can we say something there? So let me tell you. So we started asking ourselves, okay, what if I have, so now everything is LP balls. So let mu be n uniform with the LP metric. What happens if I have a uniform measure? So the only thing we were able to say is that if P is even, then the support of these is a real analytic variety and is a very similar argument to the Kerr-Hammond price. We find a real analytic function, and this becomes a zero set of a real analytic function, and that's how we prove it. But it only works for even numbers, okay? And it's because it's basically, if I had to explain it somehow, is because the square of the absolute value is the square of the absolute value is simply the square, which is a lovely real analytic function, and the cube of the absolute value is not. So the odd ones, and then imagine if it's not an integer, it's even worse. Okay, so that's why it works. So after a long time, this is the only thing we were able to produce. We learned a lot. We understand many, many things, but we were really stuck. So I thought, okay, like many times in math, even if this is what you want, maybe we need to look at something slightly different. And so here is what we started looking at. With Max Gehring, a former student of mine who currently lives in Germany, Bobby Wilson, and myself, we started looking, let's take RM with a Holder continuous Riemannian metric, okay? Let's imagine, so I'm gonna think for a second of G as a matrix, and so since it's symmetric, I write it as lambda minus 2, sorry, this is a matrix also, minus 2 squared, I know it's a square. And I assume that mu is locally finite and satisfies the following. So I'm basically looking at the balls. It's not exactly, I'm doing an approximation because I am Holder continuous. I'm doing an approximation. I'm looking at the balls in this metric, or roughly speaking. So what's the E of AR? Oh, this, I am sorry, this E here, E of 0R should have been the ball. So this is, I am very sorry, this is the ball, the round ball, centered at 0 and radius R, that you deform by the lambda here. This is lambda minus 2, so you deform plus A. So if you think this is roughly, is up to first ordered approximation, sorry, the up to first ordered approximation is the unit ball in this Riemannian metric. And the question is, if this limit exists, what can I say about the support of my measure? And so we introduce a different notion of tangent. It's called lambda tangent. So they're adapted to this problem. We study all lambda tangents. We prove that all lambda tangents are uniform. And then we are also able to prove that mu is n rectifiable. This requires a modification of prices. It's not, it's not the generality that we wanted, but it basically shows us that in the Riemannian case, if I think of Rn with a Riemannian metric, I have recovered prices theorem and metric that's just Holder continuous. The question of what happens if I, rather than having a Riemannian metric, I have something that's called like a Finsler metric, so it doesn't come from an inner product, do I have the results or not? So for the Riemannian case, we have the results. Let me first show you, given the time, but I always like to introduce my collaborators, and a picture is better than so this is David Bate doing something that he shouldn't, Max Gehring, and then Bobby Wilson. And so what's the takeaway? That the infinitesimal properties of a measure in Euclidean space with a Riemannian metric determine the structure of its support, and that the question of what happens in Euclidean space with LP metric poses interesting challenges. And because we're very stubborn, we still are working on it. Just let me finish by saying thank you very much for your attention. Muchas gracias.
Someone have some questions?
So, Brian has a question.
I have no question. I just want to thank Professor Toro to be here again. And I was giving an applause because I think it was very interesting, your talk, Professor.
Okay, so maybe I have a question, if I may. What about, say, the structure of the support of measure? If on Rn one consider one non-isotropic structure, let's say you want to find dilations, yes, weights, some weights. Is this approach for the commutative case applies also for that no commutative setting? Let's say when one take Heisenberg groups, that one has this or nilpotent groups.
So let me tell you, so the study of what happens, even Price's initial theorem in the Heisenberg group. So people have looked at what happens in the Heisenberg group and in Carnot groups. And so that's not my area of expertise, but I understand that, for example, even for the Heisenberg group, you can introduce different metrics, or you can define the metrics as slightly different. Even though you have a square here, you know, the scaling is different. You can define the metric as slightly different. And there is one definition, the metric that has a composite name. There's one definition of the metric where they're able to prove that if you are a uniform measure in that with respect to that metric, then your supporter is real analytic, and the ideas are exactly the same ones that I explained here. And it's exactly because that metric comes described in terms of the squares. You know, even I know one is a square, one is linear, but you can do it x4, x squared, and then that becomes so. But in that setting, it depends very much how do you find the metric. So some of the metrics you put works and some of them don't. Actually, only one works at this stage. Okay.
Okay. Thank you. That's all from my side. Any other question for Professor Toro? You can raise your hand and we can activate your microphone. Okay. So if not, then just let's say thanks to Professor Tatiana Toro for this wonderful plenary. So thank you very much, Professor.
Muchas gracias a ustedes. Espero que el resto de la conferencia sea un éxito y espero poder asistir a algunas de las charlas, no a las de las 6 de la mañana.
Sí.
Gracias, profe.
Gracias.
Muchas gracias, profesor.
Gracias.
Chao.
Bueno, muy bien. Entonces, siendo todo por hoy, nos vemos el día de mañana. La primera charla el día de mañana es el profesor Enrique Suazua a las 7 de la mañana, en hora de Colombia. Entonces, muchas gracias a todos por conectarse. Si mis compañeros tienen algo más que decir.
See you
Quiero dar...
tomorrow we will start with the Suazua talks at 7 a.m. Colombian hour. So let's continue tomorrow.
Ok, que yo quería decir que recuerden a los participantes que el link para cada día de la reunión de Zoom será, pues, se les enviará por correo, y al igual el link de la transmisión por YouTube también es diferente. Entonces, pues los esperamos mañana. Ya este link no va a servir y pues serán informados por correo y por la página para que estén al pendiente, por favor.
Okay, the links for the next days we will send you to your email, and also in the page, the homepage of this event will be the link for YouTube streaming. And I think creo que no te escuché una parte porque se te fue el audio. ¿Eso fue todo? ¿Está bien? Se nos fue. Pero, ¿sí? Bueno.
Okay, bye bye, guys.
Bye, everyone.